Welcome to the RQI Circuit 2026. Today we're here in Manchester. This is the 5th edition of this RQI Circuit. I'm assuming that this is working?
Yeah.
All right, so just to give some information about the RQI Circuit and what's the idea behind this. So this is a series of local conferences that is happening every Friday. Started, well, 4 weeks ago, 5 weeks ago, depending on how you count, in Stockholm. We went to Vienna after this. We went to Spain, to Ponferrada during the postdoc meeting, then Waterloo, and all of these were broadcast live in YouTube. This is an initiative of this International Society for Relativistic Quantum Information, the ISRQI. So this is a community of scientists that doesn't have any funds or any money for organizing anything, but local conferences are very cheap, and broadcasting them is not expensive either. Just need the camera and some microphones and equipment, and that I was very happy to get 3 years ago. So this is where this idea of the RQI circuit came from 3 years ago. And now this is the second time we're doing this. First time we're here in Manchester. Last time we had it in Nottingham. Cool. So if you're interested in RQI research overall, in the series of conferences, these efforts in this community, then you can register by going to this isrqi.net is the name of the website, and clicking that little key there on the top right. And that should bring you to a registration link, and you can become a part of the society and hear all about the events we organize and things like that. So without further ado, let me give it to the local organizers, Maciej and Ilaria. I think that Maciej is going to be speaking now. So please, Maciej, floor is yours. Start the conference.
Hello. Well, I'll start off on a boring note. I have just some announcements for the people in the room before we get going. So first of all, thank you for coming to the greenhouse of a room on the roof of a building on the hottest day of the week. We're trying our best to keep it cool, but if you do find it hot, it's all right to step outside, just not on the roof. If you need some water, there is a kitchen just out through the main door and on the left, and there's a cold water tap there. If you need to go to the toilets are at the end of the corridor, and then the signposts you passed the lifts on the right. There is no scheduled fire test, so if you do hear fire alarm, evacuate, even though it does say on the doors to the roof to evacuate through the roof, please do not. If that happens, please evacuate through the main corridor and down the set of stairs, and don't use the lifts. What else are the important but boring stuff? Oh yeah, and then we've got the information for the speakers. If you are speaking today, there is two main big rules. First one is please stick to time, as in any conference. The second one, because we are, like Rick said, broadcasting everything online, we want you to be on camera. So we have delineated where you can stay and still be on camera. If you go past the yellow line, that's your own fault, and you're being cut off. If you go past this desk, you're also being cut off, and that's also your fault. We have informed you. Yep, and then for the audience, if you do have questions, the only thing I ask is that you wait for the microphone so that people online can hear, and that you introduce yourself before you ask the questions. So that's all the organizational side that I've got, I think. So if we can get started with Silke.
Thank you, Maciej. Well, I just also want to say welcome, everyone. And of course, thank Ilaria and Maciej for organizing this event together with Rick. That's was a lot of work, and I'm very happy that we managed to do this and also to do it here in Manchester. Just a few words about the research you're going to hear about. Is a lot of research that has been carried out in my own research group, but my own research group includes close collaborators and friends. One of them is Jorma Louko, who's here today. Many of the work that you see is joint collaboration also. And then also very happy to announce that we have an external speaker as well. So that is Bill Unruh. Bill is here, also long-term collaborator working with Jorma and myself on the ambitious goal to see the Unruh effect in the lab. And without further ado, I think we should start with the talks. Thank you.
Thank you, Silke. Okay, so if I could call Marion for the first talk. Let's get set up.
Do I have to hold this the whole time?
No, you can pin it onto your shirt. It's probably better if you pin it.
Yeah.
check that this works.
Yeah. Okay.
Right. So please, for the first session of the workshop, welcome Dr. Marion Cromb.
Yes, hello. I'm Marion. I use they, them pronouns. I'm a postdoc in Silke's Gravity Lab group. I'm going to be talking a bit today about how that if we want to understand this problem of quantum plus gravity, it's important to understand that the way that quantum phenomena are affected by frames of reference. I'm going to be actually talking about some of my previous experiments, so my PhD experiments in Glasgow in Daniel Faccio's group and previous postdoc experiments in Southampton in Hendrik Ulbricht's group, talking with those experiments about how to alter entanglement with rotation, how to build a black hole bomb using Zeldovich amplification, and if I have time, which I probably won't, I'm going to introduce a bit about the test of the Unruh effect that we're doing here in the Gravity Lab. So whether implicitly or explicitly, all physical systems are basically measured relative to a reference frame. So in general, standard quantum mechanics requires you to split time and space to have, for example, time evolution of wave functions. And quantities and their interpretations have to be transformed between reference frames. In non-inertial frames and curved spacetimes, this can have serious consequences. So different observers can experience time differently, and then they'll have different energy operators. Their idea of what a positive and a negative frequency is going to change. The state that minimizes that energy operator is the vacuum state, and again, that's going to be observer dependent. And as the concept of particles is defined with respect to that vacuum state, different observers can basically observe the same state to have different numbers of particles. Boundary conditions are also going to change the vacuum expectation value, and all this different frame dependence is going to give rise to a bunch of different effects. Another reason to care about different frames of reference is the equivalence principle. So Einstein's principle underpins general relativity, and it relates results for non-inertial motion to results in curved spacetime and vice versa. So Hawking radiation and Unruh temperature is related in this way. So if we want to do experiments, if we want to curve spacetime noticeably, you need literally astronomical amounts of matter or energy. But to move stuff around, you can do that pretty easily in the lab. And circular motion is even more useful because your experiment won't accelerate out of your lab. So if we do these quantum experiments in different reference frames or with analogs to different spacetimes, we can combine these quantum and spacetime effects and hopefully gain some insight into this big question. So I'm particularly interested in rotation. So the experiments I'm going to talk about is how it will affect two-photon entanglement, how waves with angular momentum can actually be amplified through interaction with a rotating absorber. And again, if I have time, I will briefly introduce the Unruh effect in the Unruh experiment. So this is some PhD work. There are two main bits of physics that we need to understand: how we altered the symmetry of two-photon quantum entanglement through mechanical rotation. So the Hongou-Mandel effect we used as an entanglement witness, and the Sagnac effect is an effect that occurs in rotating reference frames. So the Hongou-Mandel, or HOM effect, is a way of seeing how indistinguishable two photons are. So when two independent photons cross at a lossless 50-50 beam splitter, there are four classical possibilities. Both can be transmitted, both reflected, photon A transmitted while B is reflected, or vice versa. If the photons are completely indistinguishable, these first two outcomes, they'll destructively interfere, and the photons will always exit bunched together, the same exit port. If we put detectors in the output ports, they'll basically measure coincidences if they both detect a photon at the same time. If we introduce a time delay between our input photons, this introduces some distinguishability. So if we scan this delay, we find a characteristic dip in coincidences where the two photons overlap in time, and this is called a Hom dip. You can also get a Hom peak in certain cases. So if you do the same interference experiment, but with fermions, because of the exclusion principle, they won't exit in the same path at the same time, and they will anti-bunch instead. With bosons, such as photons, you only get this anti-bunching, this peak, if your photons are entangled. Specifically, they need to be in a sort of anti-symmetric entangled state. So the key point here is with photons, if you see a dip, they could be symmetrically entangled or they could just be completely independent, whereas a peak requires entanglement and specifically anti-symmetric entanglement. The Sagnac effect is a special relativistic effect that creates a time difference between counterpropagating paths around closed loops in a rotating frame or in a rotating space-time. So if you consider a light beam that's split in two and each half made to follow the same path around a ring but in different directions, they should take the same amount of time to circumnavigate a stationary ring, but if the ring is rotating, the invariance of the speed of light in the inertial frame means that the counter-rotating light takes less time because the endpoint has moved around to meet it, while the co-rotating light will take more time because the endpoint has moved away. This creates a time difference and a phase difference between the two beams, and that will change their interference fringes. The phase difference between them is proportional to the angular frequency omega of the ring and also the area enclosed by the ring. So we can use the Sagnac effect to basically cause a phase shift and change the symmetry of the photons in our experiment. So this is a schematic of the experiment. We have a rotating optical table. We have a pump laser that's kind of the purpley blue box. It's pumping a nonlinear crystal that creates symmetrically entangled photon pairs. So here we're actually using frequency time entanglement, but there have been other experiments subsequently that have used polarization entanglement. So with the frequency time entanglement, to create the antisymmetric entanglement, we need to basically add multiple paths to our experiment to create cross interference, and that's where this antisymmetric entanglement will occur. So we do this with the two beam splitters that send each photon in a superposition of clockwise and anti-clockwise directions around the table. And this should create a path difference between these directions due to the Sagnac effect. The phase difference within each photon will actually change the entanglement phase between the photon pair. And then the entangled photons recombine at the last beam splitter here. And then we measure those coincidences to see if we can see the Hom and the entanglement. So the extra paths that we've added, they result in multiple dips. Our setup produced 5 dips, which always makes me think of this. And our dips number 2 and 4, they should change to peaks when we rotate fast enough to create that phase shift that's going to anti-symmetrize the entanglement. So here you can see what the setup looked like when it was spinning. It was kind of a bit scary to stand next to it because it was going about a hertz when it was max speed. And seeing how the rotation changes the dip, what we do is we just scan over that second dip each time we step up or down the rotation speed. So we observed that when we change the rotation frequency, that changes the dip sinusoidally from a dip into a peak and vice versa, with a periodicity that matched our theoretical expectation. So to summarize, when we spun our experiment, the Sagnac effect created this time delay between our input photons that changed their entanglement symmetry. So we saw that Hom interference change between a dip and a peak depending on the speed. The key takeaway here is not the specific entanglement that we observed, because there are much easier ways to flip Hom dips, but the fact that the mechanical rotation alone, so the reference frame the experiment is in, will actually have an influence on this entanglement. We also proposed experiments that should be able to actually generate entanglement through rotation in a similar way. Now for something quite different. Zeldovich amplification and black hole bombs. So about 50 years ago, Zeldovich here predicted that rotating absorbers can actually amplify waves that have angular momentum. So the effect has strong links to black hole physics and also quantum vacuum amplification. In my PhD, we showed the effect with sound waves, and in my postdoc at Southampton with electromagnetic fields, and there are experiments in Nottingham with water waves and superfluids that are also looking at this sort of thing. So Zeldovich was initially inspired by the Penrose process. So this was the idea of basically harnessing a rotating black hole as a power source. So around a black hole event horizon is its ergosphere, here in red, where all objects are going to be dragged around with that rotating space-time, but can still escape. So an object in this area can have a negative energy, and if we lose that negative energy into the black hole, the other part can be retrieved with a net energy gain. So Zeldovich then predicted that waves with angular momentum could also be amplified in a similar way. So not only by rotating black holes, but also by any rotating absorber, like a metal cylinder, for example. So in this absorber's rotating frame, waves with angular momentum are rotationally Doppler shifted. So their frequency will change depending on the rotation speeds, and this is similar to the linear Doppler shift. So normally the cylinder would partly absorb the waves, but if the cylinder rotates fast enough, then the Doppler shifted frequency will go negative. And this sign change then forces that absorption to become amplification. So the reflected wave will basically gain energy from that rotating cylinder, like taking energy from the black hole. Zeldovich also had some other insights in this system that led to new astrophysical predictions. So firstly, he realized that rotating absorbers, including black holes, should also amplify waves out of the quantum vacuum. This in turn inspired Hawking's prediction that any black hole, even if it wasn't rotating, would slowly radiate its energy away due to this interaction with the quantum vacuum. Zeldovich also predicted that by surrounding the rotating cylinder with a resonant low-loss reflector, you could basically cycle this amplification for a generation effect. So you wouldn't need any input, you could just seed it by thermal noise or by the quantum vacuum. Press and Tucholsky realized that this could be used to create a black hole bomb. So if you surround your rotating black hole with a spherical mirror, the system becomes unstable to random noise, and the resonant modes of the system that match that amplification criteria will exponentially grow over time, and that will build up energy in the mirror until it explodes, or until someone comes along and extracts it in a more reasonable way. So this led to the name black hole bond instability for this generation effect. So to make a black hole bomb, we need certain ingredients. We need to meet Zeldovich's condition. So this condition basically coincides with the modes being sufficiently rotationally Doppler shifted to have a negative frequency in that absorber rotating frame. We also need a mirror, basically to reflect those amplified modes back to the object again and again. So we basically need a cavity that is resonant with the modes that meet Zeldovich's condition. We also need the loss from the mirror to be lower than the amplification gain. That enables this exponential growth and instability to noise. Then we get a bomb. So first ingredient is amplification. In my PhD, we sent sound waves with orbital angular momentum through a rotating sound absorber, and then we measured those transmitted waves with co-rotating microphones. The absorber shifted from being absorbing to amplifying once it spun fast enough to meet Zeldovich's condition. An analog of Penrose superradiance using water waves in a draining water tank, basically simulating a rotating black hole, has also been previously shown by the group in Nottingham. In my postdoc in Southampton, we tested this Zeldovich amplification in an electromagnetic system, and we introduced resonance as well. So we gutted an induction motor, and used its three-phase stator to produce a rotating quadrupole magnetic field that would basically surround and closely couple to a rotating aluminium cylinder. And in series with each phase set of induction coils, we included a capacitor to create an RLC resonance circuit. The Zeldovich amplification basically shows up as that rotating cylinder, providing a negative resistance to that circuit. The circuit has other resistive elements as well, which will always contribute positive resistance. So one of these elements is a variable resistor, so we can actually control the amount of loss in this circuit. And now we can see what happens when we turn this resistor down. So from the transfer function of input voltage to output voltage, we get a measure of the total positive resistance of the whole system at different cylinder rotation rates. Purple is where the variable resistor has about 20 ohms of resistance, and red is where it has about 1 ohm. So in the grey highlighted region, we don't have any red data points because basically we've reached this unstable region where we get a total negative resistance. So here the loss in the circuit is smaller than the gain from the cylinder's rotation. So in that region, without applying any input signal, we get an exponentially increasing peak voltage within our circuit. So here on this log scale graph, we see it increases 4 orders of magnitude in about 2 seconds. So this runaway amplification is our black hole bomb instability. It basically increased until either the speed of the cylinder decreased because it was basically putting too much energy into the circuit and the motor that was powering it couldn't keep up. So it would slow down and that would drop it out of that region where it's amplifying. The other situation where it stops the exponential increase is if one of the resistors would reach its power limit and basically explode. So we did actually create a mini bomb, but it wasn't very scary. It just went a pop. So we put together all these ingredients in our electromagnetic system and created this black hole bomb instability. Triggering these sorts of instabilities using resonance systems can actually be a useful way to compound like very small effects to make them more measurable in the real world. And seeing this generation regime gives us hope we might be able to see sort of spontaneous generation from the quantum vacuum. So there might be different ways to do this. Some ideas is to use superconducting circuits and using basically micromagnets levitated in a superconducting trap, which isolates them from the environment and spinning them around. So we did this and we managed to spin these magnets up to about 2 megahertz. You could also use those sorts of rotating systems to test other effects. But you don't just have to do it with a rotating metal object, so you could use other rotating systems like superfluids. I know that the group have seen some black hole bomb instability-like effects in this superfluid vortex. I don't know if anyone will actually be talking about that today, but I think they're writing the paper at the moment. So I actually have 1 minute, so I might actually go to the Unruh slides, just so Chris doesn't have to introduce everything. So, essentially, this effect is if you imagine that an inertial observer will see in empty flat space-time, they'll see one type of vacuum with nothing in it. Whereas an accelerated observer will see the same vacuum as being filled with a thermal bath of particles. This is related by the equivalence principle to Hawking radiation from the gravitational field of a black hole. The problem is, to see this directly, it's very, very difficult because it's an absolutely tiny effect. Your proportionality constant basically kills you, so you need a different way of seeing this effect. And the answer is potentially with a analog system, something that has the same maths as a quantum field. So here it's a superfluid thin film that obeys an effective quantum field theory. And the key point is that we need one system that's acting as an inertial observer and one system that's acting as a rotating observer. There are other effects that complicate things, but in principle, what we just need is, let's skip through this, is two laser beams, one that is going around in a circle and one that is basically stationary and seeing if they give us different results. But there'll be more on that later, so don't worry if I've messed it up or talked too fast. So in conclusion, studying rotating systems has links to general relativity. It's more practical than constant linear acceleration. You can do a lot of cool things in non-inertial frames. I've done things mostly with very simple systems, so it's quite cool to see how we can probe this new physics with quite basic experiments in the lab. So thanks to all these people for the work on the projects, and thank you for listening.
Thank you, Marion. Okay, we'll now go to the room or online for questions.
Yeah.
Please introduce yourself first.
Hi, my name is Tamina. I have a quick question about your first part of the talk, which was the entanglement between two photons through Sinach effect and HOM.
Yeah.
You mentioned the photons, they need to be indistinguishable. I just wanted to ask if that also includes their polarization, or if they have different polarization, if you get that dip, and if you can do it with electrons with like spin up, spin down, degree of freedom, or the degree of freedom also needs to be indistinguishable.
So you repeat the question. I can repeat the question.
I'm not sure if this is what this is.
I mean, it works for the thing, but it doesn't work for the room.
I can maybe.
So the question is on the entanglement for the HOM dips and whether they need to have the same polarization and whether you could do it with other polarizations or with electrons, with spin up and spin down. So what we did was time frequency entanglement, so we needed them to be indistinguishable apart from those properties. So we needed them to have the same polarization, the same spatial modes, everything like that. Otherwise, you get less visibility in your HOM dip. So it's not like, it kind of complicates things because we have multiple dips, but if you just have one dip, you only get 100% visibility if you're completely indistinguishable. And you only get over 50% visibility if you're sort of quantum, basically, if you have a single photon state. The other group that then did an experiment with polarization entanglement, they would have, because their entanglement was in their polarization degree of freedom, their photons didn't need to have the same polarization, but they had to be entangled in their polarization degree of freedom. So if you want them to have different polarizations, you need to basically entangle their polarization, and then you can do it. But you could also do it where you were essentially erasing the information about the polarization at the end, but that would give you less visibility because you're losing half your photons. With electrons, you would get the anti-coalescence, so you get the HOM peaks if they weren't entangled. But you could, I guess, do a similar experiment where you change the symmetry and you'd get a HOM dip, and that would be your sign of entanglement.
Okay, I think for the interest of time, we're going to have to go on to the next speaker, but please thank Marion again.
Oh, yeah.
Yeah, I do.
If it connects. There is supposedly a screen there.
Is it recognizing the second screen?
Let me just find it. Let's go to duplicate instead. That might make life a little easier. No. Ah, there we go.
Oh.
Let me look.
Is it a connection?
No. Potentially. There we are. That looks a bit more promising. There, lovely stuff. Okay.
Right, after some technical difficulty, right, let's now hear from our postdoc, Dr. Chris Goodwin.
Thanks, Maciej. Okay, morning all. So my name's Chris. I'm the other postdoc in the gravity laboratory, and I'm going to try and introduce the kind of work which we are undergoing at the moment, which is all about analog gravity experiments in superfluid helium. So I have the slightly unenviable task of trying to introduce both analog gravity, superfluid helium, and the main experimental platform which is currently under development, which is going to lead us through a little bit of a convoluted pathway. I'm going to start by talking about the principles of analog gravity kind of generally, talk about what the analogy is that we're actually exploiting in these experiments. Then I'm going to switch gears entirely and take a bit of an aside to talk about superfluid helium as a standalone substance. Why is this interesting as a research topic in its own right? And then I'm going to talk about the kind of cryogenic systems that we need to use to actually develop these superfluid experiments so that we can do analog gravity. Now, the particular experiment I'm going to talk about is trying to use thin films of superfluid helium to generate the analog of a 2+1 dimensional Minkowski spacetime. And in particular, I'm going to spend most of my time talking about how we image minute surface waves that are referred to as third sound in these very, very kind of difficult to control ultra-sensitive systems. Okie doke. Let's start with analog gravity. So the analogy that we're exploiting in these experiments is the similarity between general relativity on one hand and fluid mechanics on the other. Now on the surface, these two different fields don't look like they have a great deal in common. The unifying principle here is the idea of the metric. So if we start on general relativity from the Einstein field equations, the object that emerges out of the field equations that really define everything you need to know about the system is the spacetime metric. An example might be the Schwarzschild metric, for example, which tells us the topology of spacetime in the vicinity of a spherically symmetric mass, such as a stationary black hole. On the fluid mechanics side, we start from the Navier-Stokes equations, and we impose some limiting assumptions such as incompressibility of your fluid, set viscosity to 0. You can similarly define a metric which is based on the fluid flow. So, for example, we might be talking about the bulk of a liquid, or we might be talking about the surface of a liquid, but we can define a metric which is based on the flow velocity field. And this depends on the velocity field v, but also the wave propagation speed, whether this be the speed of sound in the bulk of the fluid, or in our case, the speed of waves that are propagating on the fluid surface. Now, the similarity between these two systems that we're going to exploit is the way the metric modifies the wave equation. If I have waves of light propagating near a black hole, then obviously the way that those waves propagate is going to be heavily dependent on the shape of the spacetime in the vicinity near the black hole horizon. Similarly, in a fluid system, the way that waves propagate either in the surface or in the bulk depends entirely on the way that the fluid is moving. So I'm going to try and convince you that the waterfall is a one-dimensional analog of a black hole. Let's imagine I have an oscillator like a speaker that I place on top of the water, and I set this moving up and down. If I have this upstream in the slow-moving region, those surface waves that we generate are going to move out in all directions. If, on the other hand, I place this oscillator into the fast-moving flow beyond the lip of the waterfall, if the velocity of the fluid here is faster than the wave propagation speed, then all of those surface waves are going to be dragged downstream. So we can think of this as an acoustic horizon. An observer that's in the fast-moving flowing region cannot signal back to an observer upstream using surface waves in the same way as an observer beyond the horizon of a black hole can't signal out to the rest of the universe, even with a signal that's traveling at the speed of light. Using this analogy, we can engineer fluid flows that mimic whatever kind of non-trivial space-time topology we want. Now, previously in the group, this analogy has been exploited for simulating rotating black holes. Originally, these experiments were done in water by generating a draining vortex flow, so we now have an inflow similar to the waterfall, but we also have an azimuthal component to the flow, which simulates the effect of frame dragging around a rotating black hole. More recently, these experiments have transferred from water into superfluid helium, and the results from both of these experiments have been like, a really big leap forward in the analog gravity area. What we're trying to do now off the back of the success of these experiments is simulate something a little bit more everyday. We're trying to create the equivalent of a Minkowski spacetime, in which we can start to look for much more subtle quantum effects rather than the things like superradiant scattering or the kind of spectroscopy for surface waves around the vicinity of a rotating black hole that were uncovered by these previous experiments. Okay, let's move on to why superfluid helium. So I've already said that in order for this analogy to work, we need to throw certain variables away. A big one is viscosity. Now, that's where superfluids become a particularly useful medium. So if we look at the phase diagram of helium, first of all, helium is unique in the fact that it can remain in the fluid state all the way into the limit of zero temperature. Below what we call the lambda point, just below 2.2 Kelvin, helium transitions from a classical viscous fluid, or the normal component as we refer to it, into the superfluid component. Now, I don't really like these phase diagrams in that it shows this crossover as a sharp boundary. In reality, this is a second-order phase transition. If I plot the relative density of the normal component in red versus the superfluid component in blue, below the lambda point, the density of the normal component continuously falls away to zero in the low temperature limit, and it's replaced by a superfluid component, which is described entirely by a macroscopic wave function. Now, the normal component carries all of the classical heat, entropy, viscosity that you would expect in a hydrodynamic system, whereas the superfluid component is entirely described by the wave function. So we apply the normal quantum mechanical operators, and you get the kind of results that you'd expect. You apply the momentum operator to this, and instead of seeing the motion of a particle, say, what you're measuring is the overall flow of a macroscopic fluid. So this is a large-scale quantum system similar to a Bose-Einstein condensate. The difference is that you can create perpetual flow states in a superfluid. Now, as you'd expect, with a large quantum mechanical object, it's going to have a lot of strange behaviors. I'd love to go down the rabbit hole on all of them, but I'm going to focus on one, which is the fact that superfluids have this tendency to spread out and form very thin films, typically on the order of tens of nanometers thick. And you can demonstrate this really easily by just taking a bowl and scooping a sample of superfluid. So this is a video that's taken in one of our cryostats. This is a sample of superfluid at about 1.5 Kelvin. And what you might notice is that from the bottom of the bowl, we've got this constant drip. This is not a leaky bowl. What's happening here is that the superfluid is spreading out into a film, which is climbing over the walls of the bowl, down the outside, collecting at the bottom and dripping back into the container below. Left to its own devices, this bowl would be empty in a matter of several minutes. And we're going to use these thin films as our analog spacetime. This is going to allow us to generate an analog 2+1 dimensional spacetime in which we're going to be doing our new experiments. So I want to take a second to talk about the kind of cryogenic systems that you actually need to generate a superfluid so that you can get the wider context of how these experiments work. So in our lab, we have two cryostats. This is one of them. This is really the simplest kind of cryostat that you can use to generate superfluid in the case of helium-4. This is a helium-4 pumping cryostat, and it consists of two nested double-walled glass dewars. We start by filling the outer dewar with liquid nitrogen. This serves two purposes. The first is to pre-cool the system down to liquid nitrogen temperatures, about 77 Kelvin. And the second is to act as a thermal shield for this inner dewar, which we fill with liquid helium. Now, helium at its boiling point sits at 4.2 Kelvin. So we need to now drive the temperature down in order to transition into the superfluid phase. The way we do that is with evaporative cooling. So you can see these corrugated hoses going off into the lab frame. They lead to a vacuum pump. And the purpose of the pump is to extract all of the helium gas out of the inner dewar. Now, you can think of the helium gas as being comprised as all of the hottest atoms that were in the fluid. These are the atoms which were energetic enough to achieve escape velocity and move from the liquid phase into the gas phase. So by removing the gas, we remove all of the highest energy atoms from the system, and we systematically lower the temperature. As the pressure falls, the temperature falls with it. And you'll notice that when we go below the lambda point, that pressure really drops off rapidly. The vapor pressure above a superfluid is significantly lower than it is above a normal fluid. And as a result, there's a limit on how cold you can get this system. When you reach about 1.5 Kelvin, there simply isn't enough vapor for these pumps to work on to drive active cooling further. If you want to go colder again, we need a more sophisticated system. So this is our new fridge, which we have in the lab. And if I draw a kind of thermal diagram for this one, it looks a whole lot more complicated on the surface. But the physics and the mechanisms we use for cooling are exactly the same. So we have these copper stages going down the fridge, and as you go down the ladder, you're going down in temperature. The loop which I've drawn on the left is our helium-4 cooling circuit, and this works exactly the same as it does in the glass cryostat. We have a pot, which we fill with liquid helium-4, and a pump, which is constantly removing the helium vapor. This gives us a base temperature on this plate of 1.5 Kelvin. The difference with the glass cryostat is that this is now in a closed cycle. So that helium gas goes through an internal liquefier, which then goes back to refeeding that 1K pot, allowing us to hold 1.5K indefinitely. To go colder, we need helium-3. So helium-3 remains liquid down to the 0 temperature limit as well, but it doesn't transition into a superfluid until much lower temperatures, on the order of 2 or 3 millikelvin. The result, the vapor pressure stays higher for longer periods of time, and by pumping on this, we can achieve a base temperature of 300 millikelvin. Mounted on our cold plate, we have an experimental cell. And this is where our new experiment is being developed. So what we're trying to develop in this system is a thin film Minkowski spacetime. So our cell is a closed with isotopically purified helium-4 up to around about 4 bars. When we cool the system down, that gives us about 1 milliliter of superfluid. If we look inside the cell, you can see we've got openings on the top and bottom. These are a pair of windows which allow for optical access so that we can see what the film is doing inside the cell while the system is cold. Now, at the bottom, we have this cylindrical reservoir that sits around the bottom window. That's where we want our superfluid to accumulate. And we have this steel flange holding the window in place with some draining channels built into the side. Our window is a sapphire optical flat, and the exposed area is about 10 millimeters wide. So we fill the cell with helium, it collects in this reservoir, and then as it spreads out to form a film, it moves in through these side channels and coats our base window. Now, this creates, first of all, an analog spacetime, which comes from the film. But the surface waves provide an analog of the excitations of a scalar quantum field. This is because these are what are referred to as third sound modes. And in the long wavelength limit, these obey a Klein-Gordon equation. Now, I'm not going to go into detail of the theory of where that, of really fleshing out that analog. I'm going to leave that to Ilaria in the next talk. I want to really kind of just go through the mechanics of how the experiment works. So what we want to be able to do is to image these surface waves so that we can extract information about what's going on with the spectrum of excitations in this effective field in our closed system. And in order to do that, we use a laser probe. So by passing an expanded beam of continuous green light through the system, this beam is expanded up to about 8 millimeters. And the height fluctuations on the film get imprinted onto the beam as phase fluctuations. An easy way to think of this is if we imagine the beam to be comprised of a set of plane waves, those waves get impeded as they pass through the film, and they get impeded for longer in the regions where the film is thickest. So the result is that the waves that emerge have a map of phase imperfections imprinted onto them, which map on to the height fluctuations on our film surface. This gives us a way of resolving these surface modes with both spatial and temporal resolution, and then we can build a picture of the spectrum of excitations that are in our system. So zooming out to the wider setup, in order to read off these phase fluctuations, we need an interferometer. In our case, the technique we're using is called off-axis digital holography. So we have our laser source, which sits in the room temperature side of the lab frame. It's split by a beam splitter and goes towards 2 beam expanders to bring us up to that 8 millimeter diameter. One beam passes through our cell and then is recombined at a second beam splitter before the interference pattern is read off by a digital camera. Now, the off-axis part for off-axis digital holography refers to the fact that this second beam splitter is not aligned perfectly with the optical path of these two beams. The result is that the interference pattern, which is seen by a camera, looks like a set of linear fringes. One wavefront is tilted relative to the other, and as a result, as they cross, the phase difference between them winds in one direction, giving us this linear interferogram. Now we introduce these surface waves that imprint the phase fluctuations onto our target beam, and as a result, our interferogram gets modulated in a way which is predictable based on how it's been locally impeded at the peaks and troughs of these surface modes. Using Fourier transform profilometry, we can go from the interferogram to a reconstruction of the fluid interface. So these are some preliminary results which we currently have up on arXiv. And what they show are the surface modes of, in this case, quite a thick film. We're starting here with a film that's fractions of a millimeter in thickness. What we're actually developing at the moment are techniques to drive that film thickness down and really test what the limit of the resolution of this probe is. Right now, we're into the tens of nanometers regime, so hopefully very soon we'll have a new batch of results that we can share. Once we have this reconstruction, understanding that we have this cylindrical boundary around the window, we can decompose these waves into a set of cylindrical eigenmodes. By using frequency filtering on the original reconstruction, we can separate out these modes, and then we can fit them with cylindrical Bessel functions. We now have information on the frequency and the wavelength of these modes, and that allows us to plot the dispersion relation and compare it to the spectrum which we would expect for third sound excitations. Zooming out to the kind of bigger picture of what this is supposed to represent, we have our effective spacetime and a single scalar quantum field analog. So the way I like to talk about this is as a toy universe. We have a universe with 2 dimensions of space, one single field, and an observer that can now measure the spectrum of excitations in that singular field. So this observer can basically count the particles of different energies in their universe. This is obviously a fertile ground for all sorts of analog experiments, but the one thing in particular which we're looking for is how does this spectrum of excitations change when you shift into a new reference frame? So this is something which Marion has mentioned. The direction that we're going now is to introduce a second probe beam, which is in constant circular motion. And what this gives us is an accelerating observer, which is looking at the same system at the same time as our inertial observer, and then we can compare the power spectra of the excitations that they both perceive. What we're looking for is the analog of the Unruh effect. So our inertial observer will see either a vacuum state or some low-energy thermal state, and what we hope to see is that there'll be a shift in the power spectral density in the accelerating frame that corresponds to a bath of thermal particles that are dependent on the acceleration of the observer. Now, Marion already pointed out that the temperature shift that you would expect to see if this were just an observer out in the universe would be infinitesimally small. You'd need to be accelerating at enormous velocities in order to be able to see anything significant. But in the analog, our relativistic limit has now been dropped by 9 orders of magnitude. Our surface waves, which propagate on the order of 10 centimeters per second, are playing the role of light waves in this system. And as a result, we need much smaller accelerations in order to be able to perceive this bath of thermal excitations. Now, Ilaria is going to go into a lot more detail about what the analog is here and what we actually expect to see in the experiment. So I'm going to stop there and I'm going to sum up with a couple of key points. Superfluids are stable quantum fluids which allow for direct imaging with arbitrary flow states. Compared to things like Bose-Einstein condensates, these exist at positively exotic temperatures of 2 Kelvin, and therefore you can subject them to all sorts of external flow conditioners, which allow you to generate the analogs of some really exotic space-time geometries, whether they be black holes, the early universe, Minkowski spacetimes, expanding spacetimes. The sky is really the limit in terms of what you can simulate in this system. Because of these Klein-Gordon-like excitations that we can generate on top of thin films, this means that we can start looking for predictions not just from general relativity, but from quantum field theory as well. And because these systems exist in these closed cycle refrigerators, we can hold the system in a steady condition for long enough periods of time to collect very large data sets and allow us to look for incredibly subtle effects. I'll pause there thank you very much. I'm happy to take any questions.
Okay, thank you, Chris. And we'll go to the room for questions now. Yeah, Andrew.
Thanks, Chris. Yeah, very clear. Could you just specify what type of excitations are you talking about? Are they third sound phonons?
So we're aiming to produce third sound phonon excitations, yes. Now at the moment with the results that I showed, we're obviously in a thick film regime. So these surface modes are mostly driven by gravity as a restoring force rather than van der Waals interaction as you'd expect in a thin film. But our goal at the moment is to really focus on film controls so that we're into the third sound regime. And we are just looking at these third sound phonon type excitations, yes.
Thank you.
Thanks.
Hi, Chris. I'm wondering, have you, in that bowl that spontaneously empties because the film climbs the wall, would it be possible to estimate the speed of the radial flow towards the bottom of the bowl? Because I'm kind of thinking ahead there and thinking, well, could we already have a horizon sort of at the bottom of the bowl? Because if it's rushing in, and then maybe you could set up a horizon.
So in principle, I would expect yes. For example, if you think about the propagation speed of the third sound modes, this depends on the gradient of the thickness of the film creating a chemical potential between one point and the other. That same chemical potential is going to drive the propagation of the film. The issue is temperature control. Because if I start with a bowl of helium in the normal fluid state, and I cool down through the superfluid transition to start the flow of the film, then I'm going to start from a situation where I have a very rarefied superfluid component, which is dominated by normal fluid, and by the time you see the film start propagating, you're changing temperature. You're changing the impedance which is coming from the normal component. It's a very messy system to try and predict. The alternative would be to start in a superfluid condition, fill the bowl, and then allow it to drain when you're at a stable temperature. The difficulty is how do you fill the bowl without coating it by dipping it into the reservoir? So in principle, you could predict the propagation speed at a fixed temperature, fill the bowl and let it flow outwards, but in practice, implementing that in our system, I'm not sure how we would actually go about it. It could be done in principle, it would just take a lot of modifications to the system that we have, is the short answer. But yes, you're right, that's something that could in principle be generated.
You said it empties on the scale of like minutes or something like that, so it must be quite fast that it's going out, yeah.
The lower the temperature, the faster it's going to drain. The larger the superfluid component, the more superfluid there is to propagate. So when you cross the lambda point, this creeping of the film starts very, very slow, and then it gets faster as a function of time as you continue to cool down. So if you started at, like, say, 1.5 Kelvin, you've got about 80–85% superfluid at that point. If you could then just fill the bowl from above, say, keeping the outside of the bowl initially dry, then yes, you could start thinking about how would you calculate that propagation speed around the outside. In practice, that's quite difficult to do when you have a cryostat which just has a reservoir of helium and a bowl that you can lower down and fill. I'm not saying it's impossible, but it would be a tricky thing to implement.
Nice.
So there's actually a series of experiments that have come out of a group in Japan recently that have been looking at exactly this, looking at these anomalous pendant dripping modes that are being seeded by a rolling film. And they've been looking at the way that the kind of super wetting of the film around the geometry of the bowl affects the flow rate as it's coming off the pendant. So this is the type of thing which absolutely can be done, but it wouldn't allow you to really measure the propagation speed of a front of helium. It would more be the bulk flow that's moving through a pre-existing film. Any other questions?
The restoring force of the surface waves. It's clear that the liquid is a little fuzzy-haired guy here. It's clear that the liquid has surface tension because that the droplet is a nice round droplet, which is what you get when you get surface tension. Is that the primary restoring force for the very thin films?
No. So there is a surface tension. You're absolutely right to point it out, but it's tiny. The primary restoring force is the van der Waals interaction between the film and the substrate. So the reason why the film forms in the first place is because the interatomic interactions between the helium in the film and the substrate is significantly larger than the helium-helium interaction. So it spreads out to maximize that free surface. Now, when you're in the thin film, kind of tens of nanometers regime, that restoring force is completely dominated by the van der Waals interaction. As you then scale up the thickness of the film, the van der Waals becomes weaker, and then you get gravity as your primary restoring force, as it would be for surface waves on water.
But I'm not sure what the difference is between the I mean, it sounds to me like the van der Waals interaction is just what gives you the surface tension.
I mean, helium-helium is like the surface
Helium-helium,
tension
yeah.
in the droplet, but then I think you're saying it's the van der Waals between the substrate and the helium that's causing it to adhere.
Yeah, so the van der Waals between the helium and the substrate is the thing that's acting as an effective gravity potential, drawing down these surface waves. So by changing the thickness of the film, you change the relative strength of that interaction, and that allows you to tune the speed of propagation of these third sound modes. How much of an influence surface tension has on that, I couldn't tell you off the top of my head, I'm afraid.
So so it's the helium substrate interaction that's the main one that's giving you the restoring force.
Yes.
What's the shape of that? I mean, is it fairly linear, or?
So that's actually quite complicated. This is something that Ilaria, I think, is probably going to go into detail on, the difference. So depending on what thickness regime you're in, the restoring force either goes like the thickness, 1 over the thickness cubed, or 1 over the thickness to the 4th, depending on whether or not you're at a thick enough distance from the substrate that you need to think of retarded potentials as the thing that's driving the restoring force. So it does vary very rapidly as you change the film thickness.
Okay, so you get nonlinearities due to that. Thank you.
Thank you.
Thank you. I'm afraid we're out of time for more questions, but we can always carry on over the coffee break. Let's thank Chris again. And then we'll set up with the next speaker.
Oh, I need the adapter.
Can you check if this works?
I'll need to allow him. Okay.
You've allowed it now?
Oh.
Okay.
Which one is it? This one?
This one is forward. Okay.
Go.
Okay, and for the last session of the morning, we have Ilaria Dimina carrying on the theme of Unruh effect in analog thin films. Please go ahead.
Yeah, so good morning, everyone. So today I'll be talking more about the experiment that Chris has just explained. So it's the detector that we're developing for the analog Unruh effect in thin films of superfluid helium-4. So Marion already introduced the Unruh effect, but just as a recap, this is a prediction from quantum field theory in curved spacetime that an observer accelerating through the Minkowski vacuum will perceive a thermal bath compared to an observer that isn't accelerating. So in other words, the accelerating observer through this empty space will be able to perceive a temperature given by the Unruh temperature here, which is proportional to the acceleration of the observer. Now, this effect is incredibly interesting and important because it really lies at the interplay between quantum physics and general relativity. Detecting it would really bring us so much closer to our understanding of the universe and of physics. However, as Marion said, it's incredibly hard to detect. This is because you need really, really high linear accelerations to be able to get to an appreciable temperature. So like Marion mentioned, to feel something like 1 Kelvin for an Unruh temperature, you need an acceleration of 10 to the 21 meters per second squared, which is incredibly high. So it's for this reason that we turn to analog gravity as a possible solution to test for this effect in a controlled laboratory setting. So as we all know, predictions of quantum field theory in curved spacetime are incredibly hard to detect, if not impossible, quite often.
And analog gravity uses the mathematical analogy between surface wave fluctuations on fluids with excitations in quantum scalar fields to simulate these predictions and test for these effects in controlled laboratory settings. So these are just some examples of the experiments that we currently have in Nottingham that Chris talked about to simulate these effects. And to simulate the Unruh effect, what we're particularly interested in is the use of superfluid helium thin films, which make excellent analogs to test for the Unruh effect. So below about 2.17 Kelvin, helium transitions from a normal fluid to a superfluid. But what this actually means is that it enters a two-fluid model, like Chris mentioned, with a normal component that has viscosity and that will dissipate, and a superfluid component that is completely viscosity-free. And as you go down the temperature ladder from your transition temperature, the superfluid component begins to dominate quite rapidly over the normal component, so that when you're at about 1 Kelvin, you're already at something like 99% superfluid. So when you're at these low temperatures, you get all sorts of weird and magical effects that start to happen. The one that we're interested in is the formation of a thin film. So my drawing is a lot less pretty than the video that Chris had, but it's from a video from the 60s of the BBC showing this effect for the first time. So if you were to scoop out a bowl of superfluid helium, this will start to creep up the walls of the bowl and fall down on the outer side, forming this droplet at the bottom because it wants to maximize its surface area. So it'll start to form this thin film. And we're interested in these thin films because what happens is that the normal component of the superfluid gets clamped onto the substrate, it gets viscosity locked, leaving only the superfluid component to oscillate freely on the surface. And these thickness fluctuations of the superfluid component are these acoustic modes that we call third sound. So while shallow water waves are driven primarily by gravity, like Chris was mentioning, the third sound waves are driven by these van der Waals forces. And these produce an attractive potential, attracting the helium atoms to the atoms of the substrate, allowing for the film to climb up the sides of the wall, effectively not caring about gravity. So in our particular case, we want to consider films with different thicknesses. So not just tens of nanometers, but also going into the thicker film regime, where we have films that are hundreds of nanometers thick. So for this, we need to consider the fact that the speed of the interaction between the helium atoms and the atoms of the substrate is finite. So we need to include these retardation effects that occur because of this finite speed. So for this reason, we use this van der Waals potential here, where alpha characterizes the interaction strength of the van der Waals force, and this ds is the substrate-dependent distance, where these effects due to the retardation become important. So this could be, for example, 50 nanometers for a particular substrate. And if your film is thicker than that, then this is when you really need to use this potential and it becomes important to take care of these retardation effects. So what happens using this potential is that as you go thicker in the film, the substrate film attraction will actually be weakened and your third sound propagation speed will be lowered. So let's now look at the third sound dynamics and see how we build our analog platform. So the first thing that we need to do is make a set of assumptions. So again, we're considering quite a large range for the thickness of the film, up to 100 nanometers or so. And we're considering low temperatures below 500 millikelvin. We're assuming that there's no pressure or thermal gradient and that the fluid is incompressible and irrotational. Given these assumptions, we can linearize our equation of motion and we find an equation for the fluctuations in the height delta H at the superfluid surface. Here we have our surface tension sigma and rho is our density, and the G effective is our effective gravity term. This contains a term due to gravity, of course, that's little g, and then a term due to the van der Waals interaction strength from the potential that I showed before. But like Chris was mentioning, when we have really thin films, the gravity is effectively negligible, which is why we can drop it. From these equations, we can then derive what the dispersion relation is for thin films, and we can make the long wavelength approximation. And with this approximation, the dispersion relation becomes linear in k. And given this, we obtain our third sound propagation speed, which we can see is only really dependent on the thickness of the film and the van der Waals properties of the substrate and helium interactions. Now, given the equations of motion, we can also derive what the Lagrangian for the height fluctuations is. And what we can see is that it obeys a Klein-Gordon equation, where the propagation speed is no longer the speed of light, but this is propagation of the third sound, waves c3. And further, we can also find that the height field fluctuation is the conjugate momentum of the velocity potential. So this really is what builds our analog platform. Our thin film is our analog 2+1 dimensional space-time. The fluctuations on the thin film are analogous to excitations in a scalar quantum field, with their speed being around 10 centimeters a second, and that is the propagation of the third sound speed. So now, to be able to detect an analog of the Unruh effect, we need to introduce an effective continuous under-the-width detector that scans the superfluid surface for these third sound excitations. And there are two main challenges with this. One is that we need really high linear accelerations to be able to detect an analog of the Unruh effect. And the second is the fact that we're not in the Minkowski vacuum. Our superfluid has a temperature, so we need to account for this. So in the rest of my talk, I'll show how we can deal with both of these challenges in our experiment. So Chris already very nicely introduced our experimental platform, so I won't go into details. All that you need to remember is that this is basically a cooling mechanism that takes us down from room temperature to 300 millikelvin. And at the bottom, we have what we call the cell, which is an experimental cylindrical volume that we fill with isotopically pure helium for gas at room temperature. As the whole system is cooled, the helium will turn into a superfluid, so that when we're at about 300 millikelvin, we have a thin film that is coating the entirety of the cell, including these windows that sit at the bottom and at the top of the cell. To be able to reconstruct the height surface of the thin film, we introduce an expanded laser beam going through these windows, and that acts as our detector. But how exactly do lasers act as local detectors? So first, consider a free laser field propagating in the z direction. If it's just propagating through empty space, it'll be described by the standard electromagnetic Lagrangian, and we can describe it with this potential A, where psi here is the field describing the phase perturbation to the laser. If you now consider the laser beam passing through a superfluid, these two will interact. The helium atoms will react due to their polarized abilities alpha, and we'll get an interaction Lagrangian. If we substitute in our Lagrangian our answer for the potential A, we can expand for small laser phase perturbations, and what we find is an equation for the laser phase localized at a particular trajectory, capital X. And this is what we find for the laser phase. So this is what Chris was talking about. And it's the key point, is that there's a contribution to the laser phase due to the height fluctuations, delta H. So essentially, as the laser beam is going through the superfluid, the height fluctuations will get imprinted onto its phase as phase modulations. And using off-axis digital holography, we're able to reconstruct these height fluctuations by looking at the phase of the laser. So like Chris explained, we have an expanded beam that goes through a beam splitter, so that only one beam goes through the sample, and the two are recombined at a camera with at a beam splitter before entering the camera, slightly off-axis. We then use Fourier transform profilometry to reconstruct this height field. And what is important, and what I want to highlight, is the fact that we can recover the dispersion relation that I was showing you earlier using this technique. So we can decompose the surface of our thin film into individual eigenmodes and then plot their wave numbers against the frequency against the plot for the dispersion relation. Now, the shaded orange area here is between the shallow and the deep regime. What we really want to do next is go into the thinner film regime so that we can explore this area where the dispersion relation is linear more. But what I want to talk to you about now is the introduction of our accelerated Unruh beam. So like I was saying, it's really hard to get high linear accelerations in an experimental setting. So instead, what we want to do is get an infrared beam and place it on a uniform circular trajectory, scanning the superfluid surface. And the idea, again, is that there will be an observer-dependent phenomena encoded into the phase of this accelerating beam. And this really is the basis for the detector. So we have a laser field that acts as a continuous under-the-width detector for the height fluctuation field. And this is where we want to be looking for the analog Unruh effect. So this is our current setup. And this is what we're trying to implement. So we have, again, an infrared beam going through a beam splitter. One of the beams will go through 2 deflectors, so that it's placed on a circular motion, while the other beam gets frequency shifted by an acousto-optic modulator. The 2 are then recombined, and then they enter a photodiode. The signal that this photodiode recovers is what will contain this acceleration-dependent signal. So this will be encoded in the power spectral density as a 2-point function here of the laser phase modulations due to the changing in the height field. So we can relate this power spectral density with the response function, with a set of prefactors, a shot noise due to the laser, and this is our response function here, which contains a 2-point function due to the height field fluctuations. What's key is that because, like I was saying, there's a thermality, we're not in a Minkowski vacuum, this response function will not just contain an acceleration-dependent effect, will also contain a linear effect due to a Doppler shift as we have a detector accelerating through a thermal bath. So the challenge will be to be able to decode this response function and retrieve only the acceleration-dependent response. So from the power spectral density, our response function will contain both a linear and a circular effect, this due to the Doppler shift, this due to the Unruh effect. And what we want to be able to do is characterize what this linear response is for this C. Felipe stock, and then be able to decode the 2. So this is in the paper by Cameron Bunny, and this is actually an older model, so Felipe will be presenting a newer model. But what is interesting to see is that while at high frequencies, the linear and the circular effects match almost perfectly, in this sort of 100 to 200 hertz, we see that there's a slight difference. So this is where we'll be looking for the analog of the Unruh effect in our power spectral density. So just then, as a brief recap, we've seen how thin films of superfluid helium act as 2+1 dimensional spacetimes with their wave excitations acting as excitations in a scalar quantum field. And we've seen how we've developed a technique to use lasers as effective Unruh width detectors for these third sound excitations. And finally, our goal is to implement a circular beam into our setup to extract this acceleration-dependent signal that's characteristic of the Unruh effect. Thank you.
All right, thank you, Ilaria. And let's go to the room for some questions. Yep.
Hiya. Thank you very much for the great talk, and thank you to Chris and Marion as well. So I'm Ross Jenkinson. I'm a theory postdoc here at Manchester. I was wondering, so this is analogous to 2+1 dimensional spacetime, and I was wondering if, well, firstly, if there's any limitation on this being analogous to 2+1 or any differences compared to 3+1 Unruh effect. And also, I think, did you mention that the laser acts as like a dipole detector as it passes through the superfluid helium? Is there any differences that you have to account for in acting as like a dipole detector as opposed to a monopole detector?
So firstly, for the 3+1, is that the first part of your question? So the theory for this particular experiment was only developed in 2+1 dimensions. So I'm not sure exactly, perhaps Jorma could comment on this, what the limitations would be with the three-dimensional, in the three-dimensional case, if any.
It's different.
Yeah. Yeah, so we are only really looking in the...
Back to the conversation. So you need to know you can derive it in 2+1 and you can derive it in 3+1. And that also depends on where you're looking for your signal. In fact, in 2+1 it is a bit more complicated. Because where do you have a measurement, and where in this measurement hides the Unruh effect, okay? And then how do you extract it? It depends on the dimensionality. 3+1 would be nicer, because easier to extract. However, harder to implement experimentally, not because you would have a point light detector that would have to go through a 3D system. So, give or take, this is what we decided to do, and it should, in principle, be possible to extract it. Now, one of the big major developments which we did sort of as a first theory paper with Jorma and Bill was to see how can we build, a particle detector that can be implemented in an experiment. And yes, the initial detector that Bill came up with was a very much a theorist's approach, which is a two-level detector that can be excited and de-excited. Okay, so two-level detector. What we had to do is to say, how could you build something like that? And there are proposals people working on for ultra-cold atom systems where you might have a two-level detector. This is not what we're doing. What we're doing is working with continuous laser beams. Okay, so this is not a detector with a single frequency gap. That's one that can potentially probe the whole spectrum. One of the collaborators on the team is Jörg Schmidtmeyer, and he famously said the physics shouldn't depend on the detector. And so the first thing that we had to do is, or we had to basically extend this concept from the two-level detector to continuous field detectors. And you have a lot of freedom, but of course every time you change something you need to be very careful. This is why there are a lot of theorists on board to sort of make it happen despite all the differences.
Yep. So these height fluctuation third sounds are only happening in 2D film. But what we can do in 3 dimension is that instead of looking for height correlation function and calculate the power spectral density response function, we're going to be looking at density fluctuation, which also tells us about like the quasi-particle excitations. So we're just going to be looking at the order parameter for the helium, which has the density part and the phase part, and then what we're going to look at is density fluctuation. I don't know if anyone has done it with laser being the detector, but I know that you can see excitations for density fluctuations through other methods like neutron scattering or like other experimental methods that they can also tell you about the power spectral density of the excitations.
Okay, we're going to have to stop with the questions, but we can carry on over lunch. Let's thank Ilaria again. And we'll reconvene in about 60 minutes. Okay, welcome back everyone, everyone in the room and everyone online to the second session of our RQI circuit in Manchester. And as our first speaker, we're going to have Julian Hanby, and joint with some surprise guests and Ben Carter as a sort of careers development section of this workshop. So please take it away.
Hello everyone. Firstly, I'd like to thank American engineer Willis Carrier. Willis Carrier invented the first modern electrical air conditioning system, and we have one in this corner of the room. Without it, I think we would be sitting in an air fryer. So I would also like to thank Chris for arranging for that box to be in this room and at least making it vaguely bearable for us all today. So as Maciej said, in a few minutes Ben is going to talk about the University of Manchester, so a lot of the practical things that you'll need to know about if you're interested in studying or working here. I'm going to talk a bit about the engagement activities that the Gravity Lab runs, and also my colleagues Ilaria and Lucas are going to tell you a little bit about their experiences of working as part of the group. Finally, Silke, our principal investigator, will talk about the ethos for the group. So I'm Julian and I'm the project manager. So my background is in the arts and heritage rather than science. Obviously, you're hearing a lot about science that's going on, science today, but the Gravity Lab also has an active engagement strand that I support, as well as helping with the day-to-day needs of the project. So one of our key outreach programs is Photon Bricks. So this scheme provides interferometers free of charge to schools around the UK. But the really cool bit about it is that the kits are made out of Lego. They're working interferometers that produce visible fringes, so the young people get to experiment with equipment that otherwise would be out of reach for most schools in the UK. And as you can see from the map here, the reach that we have with the schools is really well spread around the country. All of the blue schools, all of the schools marked in blue on there are what STFC counts as wonder communities. So those are the communities that perhaps otherwise would have a deficit on equipment like this. So lots of schools use the kits in different ways. For me, one of the most successful ways that they use is that a sixth form group will borrow them, and interferometry is on the syllabus for sixth formers in the UK. So the sixth form group borrows an interferometer, learns how to use it, but then at a school event such as a science fair or something like that, the sixth formers then explain interferometry to the younger students. So that for me is a real win-win. They're not just learning about interferometry, they're also learning about being science communicators. We also attend events around the country demonstrating the interferometers for people of all ages. So we've been at the Edinburgh Science Festival, the Royal Institution, the UK Parliament, and this summer we'll see us take the kits to the International Scout Jamboree. When I heard about that, I thought I was going to get to go somewhere very exotic, somewhere in the world, but it turns out it's at Stoke-on-Trent. So a little bit less glamorous, but I'm sure it will be great. So all of the information that you need to build your own Lego interferometer can be found on our website, including a complete list of the bricks. Now obviously, being a Lego project, we have a Lego QR code. So if anyone wants to try and scan it now. I'm interested to see whether it works online. So if someone can scan it on a screen while watching this. If so, it's a real success for Lego, I think, for Lego as an organisation. So I'll leave it here and perhaps people can try later on as well. So next, if any of you are able to visit Jodrell Bank, it works. Someone said it works, as if we'd bring a QR code that didn't work, especially when it was made out of Lego. So if any of you are able to visit Jodrell Bank between now and September, as well as seeing the amazing Lovell telescope, you can also see our exhibition Cosmic Titans. The exhibition was first shown at Lakeside Arts at the University of Nottingham. Since then, it's been at Science Gallery London, where it was titled Quantum Untangled, and now we're at the University of Manchester's Jodrell Bank. The works are a result of collaboration with artists with an interest in understanding and communicating complex scientific ideas, and a passion for work that exists where art and science meet. The Cosmic Titans touring exhibition was made possible thanks to the Art Lab, a space that is for collaboration, that is as active a part of the Gravity Group as the science labs. But Art Lab is more than just a room. It's an open-ended way of working that welcomes diverse thinking and new approaches to scientific discipline. As the group finds its home in Manchester, our aim is to continue to embed Art Lab activities in our day-to-day work. So, what is our day-to-day work? Well, I'd firstly like to invite Ilaria to talk a little bit about her experience as a PhD student with the group.
Cool. Hello again. My name is Ilaria. I'm a second year PhD student in Silke's group, and I am Italian. So I guess I'll tell you a little bit about my day-to-day in the group, what I like about it, and what attracted me to it. So my background is entirely theoretical. I did my bachelor's in physics and philosophy, actually, so I didn't do any labs, nothing experimental. All of the lab time was substituted by philosophy, which I really enjoyed. But then I decided to go into physics, so then I did a master's called Gravity, Particles and Fields. So again, super theoretical. And then I did my master's project with the group, and I really enjoyed it, and I ended up staying for a PhD. And on the first day of my PhD, Chris handed me a screwdriver, and that was the first time I held a screwdriver. And so then I was like, okay, I guess I'm doing experiment now. And I ended up really enjoying it. So I think that really surprised me, and it was really scary at first, but then the more that the PhD progressed, the more I started to enjoy the experiment, but also doing theory, and then I picked up some data analysis as well. So I think what I've been enjoying the most is just that no one day is the same. Sort of like every day I can pick a task that I can do that's very different, work on the experiment, work on the theory, work on the data analysis side. But what sort of brings everything together is the fact that it's all collaborative. So I'm not doing any of that alone. And I've really been enjoying this aspect of the group. It's a very international group as well, so I felt very welcome being from Italy too. I mean, there were like 5 Italians when I joined, so that was pretty good. And other than that, then the collaborative aspect with the research, there's also the collaborative aspect with the outreach. So I work with Julian as well on the photon bricks, where we've taken the LEGO interferometers into schools and festivals. And I also organized with Breagh, Leonardo and Silvia an event last week in Manchester on science communication. So it's been really sort of amazing to get to do different things. It's not really your standard PhD of, you know, you're sort of alone in a room studying, occasionally collaborating. Like every day you speak to people, you engage with people. So I guess those are the aspects I've enjoyed the most.
Thanks, Ilaria. And now here I'd also like to welcome Lucas, who's visiting the group. You can either clip it or just hold it.
Yeah, I'm going to just hold it. So my name is Lucas. I'm a visitor. I'm a PhD student from Brazil. I'm visiting Silke's group for 1 year. So the way I got this visiting possibilities, because my background is in analog gravity. I started to work with analog gravity in my undergrads, but in nonlinear optics, a different kind of system. And then I got my first possibility to visit a group in Spain, in Valencia, in which I changed a little bit my research to fluid-like analogies. And now I'm working with Professor Mauricio Richards, which is a long collaborator of the group, and that's why my project now has a big overlap with what the group does. In Brazil, we have these fellowships that fund students to go abroad, and the idea is that if you pass enough time with another group, you get to see the dynamics of the group, how they approach work, how they approach research, and the idea is that you get the positive things about the group, and when you go back to your own group, you implement these things to improve your work environment. So that's one of the things that I'm doing here. I'm observing the group, and specifically about the group, what I like is that they work in such a different categories of such a different areas. They work in interface between very areas, and this way you get the opportunity to immerse yourself in different areas and different subjects, and you learn a lot. So you have quantum field theory, you have general relativity, you have theory, you have experiment, and this way you can broaden your area of research. And there's also art projects. So my day-to-day life in the group is like talking to people, talking about new projects and new ideas that are not just narrowed to my area of expertise. That's it.
Thanks, Lucas. And now I'd like to hand over to Silke, who's just going to talk a little bit more about her vision and the vision for the group. So you can just click it on.
Oh, this is a good spot now, but I have to, yeah. Okay, good. Right, so I want to share my 2 cents of wisdom with you. So I think the only reason to form a group is that the people who form it benefit from it. So I think anyone that joins a research group, any group, a friendships group, any group you join in life, you should get something out of it. You should have some positive, experiences from forming the group. You should also give back to the group. So when it comes to research, of course, this is not just, this is not just a hobby. It is for many. It is also a career path. And so when people join, they have to find their journey. They have to come out of this with more than they went in. They have to have experiences, they learn skills, they have to grow, they have to face the things they're not so good at, and we all have that. And so you need to create an environment for this, and you need to create an environment where you feel safe, where you feel encouraged to grow, where you've been told when there's something that doesn't work and you need to face it. We all need to do that. It's part of the journey. And I also believe, because the way my personal journey is, I was very lucky. I always worked with people, senior people, that let me carve out my own piece or my own journey. And so I think when you come, if you've been handed a screwdriver and you get an allergic reaction, clearly you shouldn't be doing experiments. But if you might find out things about yourself that you didn't know. And so maybe you realize, actually, holding a screwdriver is pretty cool. And so this is what it is. There should be a little bit of freedom. There is guidance, putting the supervisor head on. So there has to be, it has to be an environment of growth. And I think that is pretty much what we're trying to do.
Great, thank you. Thanks to all three for just giving a bit of an insight into the group. Hopefully that gives you a bit of an overview about what we do and how the group works. Obviously, universities have dozens of groups. We're talking about ours, but I'm pleased now to be able to hand over to Ben, who is, we'll have to do a little laptop swap over, but Ben's going to talk more specifically about the careers options at the University of Manchester. So you just plug that one anyway.
Just as a quick announcement, because we have classified this as a joint talk, any questions will be at the end addressed to both speakers. So if you have burning questions, do try to keep them until the next
speakers.
Indeed.
Oh yeah, true. Sorry. So do try to keep them for the next 15 minutes or so.
Amazing. Good afternoon, everybody. Hello to the millions on camera. Wherever you are, we hope it's less sweaty than it is here. And if are we recording this for the future? Oh, then people of the future, same to you. But for now, that was actually incredibly heartwarming for me as a lapsed researcher. So I should do a quick introduction. I am the careers consultant and postgraduate lead for the Department of Physics here at the University of Manchester, but I used to be a researcher in a similar position. My time in research was in materials chemistry. But it's easy to get quite jaded about opportunities in academic life, but to hear about the outreach, the sense of community in a group is really encouraging, and I think we need more of it in academic research. And I'm going to dig into that a little bit. I've got a few things to show you around opportunities within Manchester, but many of the things I'm going to put up on screen will be resources which anybody can use. There's going to be a flurry of QR codes, but If the slides get made available later, anything that's up on screen will be linked as well, so you just have to click on images within the slides and find whatever you need there. You don't have to be clicking QR codes all the way through. But let's start as we mean to go on. So, depending on which stage you are at within your academic career, if you're an undergraduate considering your PhD options, then you have but to scan the QR code up on screen. That'll take you to the PhD portal for physical sciences and engineering at the University of Manchester. That will give you a rundown of the projects that are available. So if you already know where your heart lies in the kind of research, then you probably wouldn't be at this session if you didn't, but it enables you to see what's out there. If, however, you're at a later stage, if you're already a PhD within the group, you want to explore postdoctoral opportunities, then you have the other section there, which takes you through academic opportunities within the University of Manchester. That's all lovely, but it's much bigger than that, of course. And I'm not here to promote the University of Manchester as a place to work. It's great, don't get me wrong, but there is also a lot more there. And again, if you want to spread your net wider when it comes to where to undertake your research, the findaphd.com website does exactly that. It also gives some excellent insights into what it means to conduct research in different parts of the world. A lot of what I'm going to talk about has a focus on the UK, but obviously you've got to go where the research is in order to succeed. And if that happens to be on the far side of the globe, then there are some good pages on findaphd.com on research cultures in different countries, how to get a PhD there. Likewise, the central repository for most, I'm going to qualify that, most academic posts within the UK is on jobs.ac.uk, and that should be supplemented with some focus on what interests you the most. I kind of want you to go to the source. If you are going to seek out full-time roles in research, you shouldn't just rely on what's on jobs.ac.uk. As I'll get to later, I think we're living in an age where the speculative approach to job hunting matters a lot. That is to say, going out and sourcing the opportunity for yourself. Finding the supervisor that you think would be the best one for you and asking them, do you need a PhD student? Do you need a postdoc? Whatever it might be. Do you need an outreach coordinator or a research coordinator for your group? These are all good questions to ask depending on what you want from your career. With that in mind, I suppose my second admonition is seek out your careers service. Now, if you're a UOM student now or in the future, or indeed member of staff, there's resources you can access. I'll talk about our careers service, but if you're at a higher education institution anywhere in the world, you probably have a careers service. Now, our offering is that if you're a student here or you are within 2 years of graduation, we will see you. We will come talk to you and we will provide you with our guidance. And I think one of the most underrated things we offer is a human being. It's a chance to talk through what's on your mind. Now, I was about to say lots of good advice on the internet. We all know that's not really true. But there's advice on the internet. And then there's the opportunity to explore that with somebody who is prepared to be unbiased, non-judgmental, and give you the space to talk. So those things relating to your career direction, to the applications you're actively going to make, or your ideas relating to interviews. If you just want to practice and sit down and have somebody bounce questions off you that you might encounter in your next interview, then we'll do all of those things and more. There's also the thorny question of if you're an international researcher and want to explore your options in the UK, then we will get you started on that. We don't pretend to be career experts, but we know some people who are. We partner with a law firm in Manchester who specialize in immigration law, and we can refer you to them as the need arises. But I think that on top of all these things, I wanted to flag up a couple of pages that if you're only just now starting to explore what it means to apply for postgraduate study, then there's a certain amount to take in. You need to be able to understand what it means for you and for the supervisor that you'll be applying to for a PhD. And we have an excellent page that will take you through what to expect in drafting a personal statement, understanding how to source your references, those sorts of things, and all the questions you should be asking yourself throughout that process. There is also an excellent page on if you're already a PhD student, some of the career questions I would like you to be asking yourself when it relates to the opening years, the central part of your PhD, what happens next, and how you explore that as you go along. That bottom QR code will take you to that page. If you do want to go straight to international options and understand those a bit better, then please scan away. This will take you to our sources when it comes to working in the UK, understanding the core visa options that are open to you, of which you have more than most as a PhD graduate. Because I think it's important to be realistic about job prospects and to understand that it is incredibly competitive finding work in academia, I encourage everybody to consider what is their plan B. International or home student, I think it is worth exploring that and understanding what would you do if your academic job search fell through? What are your next stages? I think a figure I think it's necessary for everybody to know is that 90+% of PhD graduates don't work in academia. I'm a prime example. I suppose actually no, I'm somewhere in the middle, I suppose, since I do work in higher education still. Going back to academic careers though, again, resources I'd like you to have. First of all, seek out your research and development team. We have an excellent one here at Manchester. You probably have one within your institution as well. Research and development usually sits outside of the careers service in a given university, and I've spent time as a researcher developer in other institutions. They're the people responsible for helping researchers, PhD students, postdocs, staff, all explore their potential and build on that in order to, usually, to further their academic career aims. They do look at the non-academic, the meta-academic career directions as well, but the resources I wanted to talk about really relate to academia. And to that end, I encourage anybody going through the PhD process to consider these 4 areas. Obviously, your research, and with that comes some of the things we've heard about in terms of the impact of that research, the outputs, which is to say, obviously, the research and the publications, the conferences, but the outreach, the community that you get engaged with, how that research gets communicated. These are wonderfully humanizing aspects that allow academic research to get out there into the world. If you do want to make it in academia, I think at least some point you're going to have to teach. It might not be the thing you want to do full-time, but please make sure that when you begin making full-time applications for lecturing posts, that you understand what's expected of you as a teacher, understanding your pedagogy when you get out there into the world. Money does come down to the money eventually. There's a lot of sources. The one up on screen there, Research Professional, is one of the best databases I've come across when it comes to exploring postdoctoral, early career funding sources, and others beyond when you get past that first fellowship stage and you're looking to explore some of the bigger grants that are out there. Then Research Professional provides a really good link to that. I've also flagged this thing called the Alternative Guide to Postgraduate Funding in case anybody wants to try it out. Again, if you're at UOM, you'll have access to this, but check whether your institution subscribes to it. It's a lot of different charitable funds which can supplement your research at different points. If you find a conference you desperately want to go to, then get the money. Go do it, please. The final thing on this slide is the Gateway to Research. It's the database of the UKRI's funded research around the country. I think this is a hidden gem, and I recommend it to anybody who's exploring their research or academic career options because it gathers together everything that's been successfully funded around the UK, and that information is fascinating if you wish to build a career in a particular area of research. Seeing who else has received money, and when, and why, and how much, and what did they want it for anyway? This is really interesting stuff. So the Gateway to Research database on the far side there, please take a look. It's a fascinating resource. I mentioned research and development. This is the ResDev team at Manchester. If you wish to reach out to them, they often run workshops on different aspects of academic life and how you develop as you go through your PhD, your postdoctoral years. That is specific to this university, but again, you probably have one if you're at a different institution. You definitely, I suspect, will have access to at least one of these resources. The Prosper resource for postdocs is relatively recent in the grand scheme of things, but is trying to provide a through line of development for postdocs because it is quite it's a tricky time in your career as you're trying to establish yourself as a researcher, but also trying to earn money and find that full-time position as a lecturer. So the support available through Prosper, I think, is well worth exploring. And then more generally, the Research and Development Framework, the RDF, something which was created by a group called VTI here in the UK. They're the group that champions research and development. And their tool, the RDF, is to try and help you understand what do you take away from the research process. So that if you do find yourself considering, okay, how do I articulate the skills derived from my PhD, they have a tool to help you do that and to find the language you need to help others understand it as well. This wouldn't be a careers talk if somebody didn't mention LinkedIn. And quick show of hands, please. Who is on LinkedIn already? Good. Everybody else out? No, it's too hot. We can't do that. Please connect with me. Please connect with my colleagues. Please connect with each other. LinkedIn is only as good as your network to an extent. Although the resource I've linked to on the far side of the screen, I think is one of the few things that you can utilize on LinkedIn without being too involved in the relentless backslapping which characterizes LinkedIn at the moment, the toxic positivity, as I like to call it, of LinkedIn. And the alumni tool is, I think, again, a hidden gem. It's one of the unsung heroes of LinkedIn. If you find any higher education institution on LinkedIn and click on the tab that says alumni, it will filter everybody that's graduated from the institution and then let you see where they work now. That, on its own, is fascinating, but as soon as you start to drop in such things as the keywords about your research and see where have people gone who have trodden a similar path to yourself, it is glorious. Single best thing they've ever done. As soon as they realize it, I'm sure they'll monetize it and we'll lose it forever. But for now, make the most of it. Final thought on speculative job searches. I think now more than ever, because we are in an AI-driven jobs market, and applications are up. Vacancies, sadly, are somewhat down, thanks to global events. We'll leave it at that. Going and sourcing opportunities for yourself has never been a more viable option. I'm a big fan of making phone calls where possible, although within academia, that's less possible. Emails if you absolutely have to, but basically go seeking the opportunities. Ask people if they need someone in a new position. It's worth bearing in mind that you will get more no's than yeses through this approach. It is good to remain resilient through that. But I think there's still a lot you can derive from somebody saying no to you. Just asking, can I get back to you on that, is well worth it. Understanding that there may be other people they know that you should reach out to. This is all part of the speculative process. And finally, occasionally, it pays off. You've got to be ready for that moment when somebody says, wow, thank you for calling. We desperately need someone. Let's talk all about you. And suddenly it's an interview. So be ready for that moment too. Have the necessary materials open. Do your due diligence to understand why you even called these people in the first place. Folks, that's nearly it from me. One final slide so that if you do want to explore areas beyond this, I could talk for an hour or more about non-academic careers, meta-academic careers, what that means, and the different directions you can go. But the main message here is make the most of the time. As you go through your research years, I think there's a lot you can do to seed the next stages, academic or otherwise. Start early, understand the different paths open to you, and treat it like a job as you go through. Obviously, if you stay in academia, it will become your job. But I encourage everybody to think of their PhD as a professional experience. You're doing it full time, 3, 4, 5, longer years. And I want you to reflect that in your CV and your interactions with your next employer when that time comes. You are a professional researcher when you leave the PhD, as well as an expert in your field. That is it from me. I think we're going to turn it over to questions at this point.
Let's first invite Julian back and thank both speakers of this session. And if Ilaria, Lucas, and Silke want to be nearby at least to answer questions, if those are specifically to you, then please be ready. So let's first turn to questions from the room. Anything? Right. You will be off camera if you do that. Strategically placed. So maybe I'll start us off. Julian, you did talk about a lot of sort of the opportunities of why you would want to join a group, and then Ben told us where to look for them. What about things that are maybe less specific to Manchester and like within Manchester, very much specific to our group? If somebody's very much interested in our research, what do you recommend?
I don't know. I think the key thing really would be to get in touch. As I sort of mentioned about the art lab, it's very sort of open-ended. The project, as it is currently in Nottingham and moving to Manchester, sits between mathematics and physics. It sits between experimentalists and theory, and so there is scope within the project to kind of come in a lot of different ways. So. I mean, Chris, for instance, has often said that one of the things that he really likes about a group like ours is that someone comes as a theoretician but then ends up learning real practical skills that help them then to kind of apply their theory more rigorously. Because not only are they working on the theory, but they also have a real clear understanding how the practical side of the experiments works. Is that fair to say, Chris? I think so. And I'm sure Silke can add to kind of why you would specifically come to our group. Is that sort of what you were asking? Yeah.
I think Chris just wants to convert every theorist into an experimentalist, no? Yeah. No, I think that career paths are not always straightforward. So, of course, if you go through you do a PhD and then, for a postdoc and try to go down the academic route, it seems very clear. But even along that journey, you might, you see some people change direction, research direction, reinvent themselves, end up somewhere completely different where they thought they would end up eventually. And I think also, it's not as easy if you study medicine, you might become a doctor. It's not such a straightforward answer. If you study physics or mathematics or sciences in general, there are many career paths that you can go down. There are also some that are completely, unexpected. And I think that is also a little bit of the nice thing, is kind of to see what, not what you had in mind, your sort of 5-10 year plan, but as you go along, you change. And you open up to new things, you meet people, you talk to people, you learn skills which maybe are not the main skills, but something on the side, and you can make a career out of it. So I think that especially since the world is changing so fast, AI, we all talk about, we're all worried about, we all use it. So I think that you have to have an open mind. And sometimes over-worrying can be damaging. And sometimes you should just, enjoy the moment, learn and work as much as you can, and see where it brings you.
I suppose an additional thought to all of this as well is that a group like ours isn't necessarily for everybody. I think it's really important to remember when you are on a PhD. No, being completely honest, just remember when you're on a PhD interview, as much as anything else, you're checking out whether they're the right fit for you. And I think that's really important. I'm not saying that our group isn't for anybody. I'm just saying for some people it's not the approach that they're interested in, and that's absolutely fine. Come and visit us. We'll welcome you anyway. Do you have any more career-based?
Just to reiterate the point around careers are not linear. Occasionally you'll find a job for life if you're lucky enough. Are you lucky? That's another question entirely. However, squiggly careers, please Google it. It's or whichever your search engine of choice. The sheer randomness of what directs people's career path is fascinating. It's created my favorite career development theory called planned happenstance. And whenever you talk to somebody about their career direction, at some point they'll say, "Oh, but it would never have happened unless this person hadn't said to me." So yes, embrace the unusual things that come along. Be curious, be flexible, be persistent, be optimistic. Maybe take the odd risk so that it's hard to get by entirely without it, but even the things you fall down from, you do get a chance to drag yourself back up from.
Right. Thank you. Is there any questions in the room that people had some thoughts? Yeah, Rick?
So say that I would like to come to Manchester University, say with my own money, after applying for something, either in the UK or somewhere else that is available, what would be the, say, grants or fellowships or things like this that someone could apply to come here because they're interested in the research that is not only specifically done in Silke's group or in the Gravity Laboratory, but also around that they would like to be here to collaborate with these people, but they would like to come to have the freedom to collaborate with everyone and still be able to, you know, not necessarily work for a group, but start really an independent career journey. So what would be the resources and the fellowships available for this?
Then I suppose this is you.
I don't know if I can easily name individual grants here. I suspect there's going to be a proportion of ECR, early career research grants, that some may want to explore, but depending where in the world you're coming from, exactly who that's awarded by, I think is going to vary enormously, depending on which research councils you approach. This is why I put up that link to Research Professional as a resource to explore this, because they do allow you to filter based on pre-doctoral, post-doctoral, early career, foundation grants, things like that. That is probably the best resource I can suggest for the time being, rather than trying to pin it down to individual grants, I'm afraid. Unless anybody else in the room wants to name their favorite grant, and we'll take it from there.
Manchester has a own fellowship scheme. Does anyone remember how it's called? There's this internal 3 or 5 year fellowship. What is it called again?
Kathleen
Yeah.
Orenshaw? Dame Kathleen Orenshaw,
Yes,
that
yes.
one.
So that is how long? 3 or 5 years?
I don't know, sorry, but I think that's the resource you're
Does
referring
anyone
to.
know? 3 years or 5? The Dame...
Dame Kathleen Orenshaw, I think it's called.
3 years. Yeah, so this is a fellowship where you can apply to join. It's not a permanent position, but it's an independent research fellowship. That is, you know, one way which is unique to Manchester because it is our own fellowship scheme. And then we have, depending on the discipline, we have, you know, fellowships like Ernest Rutherford in STFC area. We have the URFs from the Royal Society. University research fellowships. So there is a number of independent fellowships that you can apply for with a UK institution to start your own research group. In some cases, these lead to a permanent positions. In others, they don't, depend on what kind of grant you're winning, or also what sort of the arrangement is or the policy of the university. But the UK is pretty good at this. So just to say this, we have a number of independent fellow scheme, a big number, and usually the people that win one of those, they do end up in a permanent position.
I do have one other suggestion. For those who are looking at PhD options within Manchester, one scheme I suggest taking a look at, if you like the idea of teaching, if you don't mind having that as a significant part of your PhD experience, what's called the PGRTA, so Postgraduate in Research Teaching Assistant Scholarship, is something you may want to take a look at as a way to fund your PhD, because it allows you to just throw yourself more into the teaching process. You just get more of it. It's considered it's gently recommended to every postgraduate student that they do some teaching. They become a lab demonstrator or similar, but as a PGRTA, you actively get involved in that and make it more of part of your career.
I want to mention one more thing. So there's one nice scheme for, this is going back and forth now. So there's one nice scheme for a PhD fellowship, which is called the SPY program, which is run at the Photon Science Institute here at the University of Manchester. And that allows people with unusual career paths to conduct a PhD studies. And that would be, for example, someone who was in industry for a while, perhaps someone on maternity leave, or in our case, we have an artist joining our group in October to start his PhD, and that's through this particular fellowship scheme. And I think there are a number of fellowship schemes. If you go through the pages, they're probably all listed. So there's a lot on offer. You just need to find the right for you, I'd say.
What was the name of that one? Sorry.
SPY.
I think we're going back to Manek. I think we're out of time.
I think that would be it for this session. So let's thank all the speakers of this careers session. Okay, and now we'll welcome our next speaker, so Felipe. We're going to get you set up.
Say hi to my parents. Yeah. Okay.
Okay, so now we have Felipe Portales-Oliva continuing the idea of looking for the Unruh effect in thin films of superfluid helium. Take it away, please.
Yes, thank you. My name is Felipe Portales. I am a postdoc officially in the Theoretical Physics Institute of Sao Paulo State University, but currently I am visiting the University of Nottingham, particularly working with Jorma and the Gravity Lab people. And I want to thank you for the opportunity of speaking in this talk, of giving this talk. So, I want to start with something like a story. The day that I arrived in Nottingham, the 2nd of March, I went to Jorma's office and he told me, we have the model that you know from the papers, but we need to improve certain aspects of it. We have someone already working on this, but can you collaborate? And that is very much the philosophy of the Lavity Graph. Everything is collaborative. We have been working on this with Samin and Ilaria very profoundly for the last few months. So the title of the talk is the detector model for the 4 helium thin film in different dispersion regimes. The different dispersion regimes, keep it not in mind, but we're going to get to that. So I want to start talking about the detector model that we're going to be dealing with. As it is a quantum detector coupled with a quantum field. In this case, let us consider a 2-level detector model spawned by 2 states, 0 and 1, and those have an energy gap E between them. And that detector interacts with the field phi. But in being rigorous, we are not going to be interested in a regular Unruh DeWitt detector that couples exactly with the field. We are going to be interested in the case where the interaction is coupled with the momentum of the field. So that's what you see in the expression for the interaction Hamiltonian. I don't have, if you know the, oh, sorry, I see that. If you know the theory behind Unruh DeWitt detectors, you have a coupling constant, a switching function, the field in this case replaced by the momentum that's evaluated at the trajectory the detector is going to follow, and the detector monopole. With this in hand, we are able to compute what is going to be the transition probability of the detector. And the most important part that codifies this probability is this big double integral that is what we call the response function. In this case, as our detector is coupled with the momentum of the field, we can reduce that expression using what we call the twice-derived thermal Weidmann function, evaluated at the trajectory, of course. But this object, the response function, is what we are interested in studying. Formally, as I already said, the response function is heavily dependent on this twice-derived thermal Weidmann function that is usually defined as a 2-point correlation function in the thermal state. That's why there is a beta right there, signifying the coldness of the quantum state. And we need to evaluate it at the trajectory. Doing some simplifications based mainly on the fact that the thermal state is stationary with respect to the killing field, the time killing field, and is isotropic on the xy plane. We can reduce that horrible double integral, taking out the switching functions, considering an infinite interaction time, to this expression right here that looks more manageable. And why is that important? First, why is that important in the helium that the gravity group has for the experiment? Well, the detector model that we are applying is very well suited for the predictions, to study the predictions of what they are going to see, as in the helium, the height variations that they're going to see due to the third sound waves is exactly the canonical momentum when you study the quantum field theory in the helium. Therefore, this response function that you can compute is the same that Ilaria mentioned in her talk when she explained that the spectrum that you obtain from the measurements, the spectrum you obtain from the measurements is exactly the response function, or should reproduce the response function. Sorry. If we want to throw all our mathematical machinery into it, we can expand the 2-point thermal Weidmann function, evaluate it at an arbitrary point, and we can find an expression that looks kind of manageable. Now we would need to evaluate the trajectory and find the function, this function, to actually find the response function. Things to mention here: quantities that are due to the helium, like the density and the effective gravity model that Ilaria discussed, appear as factors in front of it, and the thermal state influences the measurement in the two blue places you see. The dispersion relation, I left it as something arbitrary at the moment, but we will see the case of linear dispersion that we are interested in a bit. The only assumption I'm going to make for the moment is that the dispersion relation is isotropic, meaning that the dependency on the wave vector is actually only going to be on the modulus of the wave vector. Now, let us focus on what happens in the helium. This is an illustrative image of the thin film of the helium. The surface waves don't actually look like this, but I draw them like this for a reason. You're going to have the variations on top of it, and the laser is going to be interacting with it. But something interesting already can be drawn from this. If you see, there are many small waves that I drew, and many that are smaller than the diameter of the laser. We are not going to be able to resolve this in the experiment. Therefore, this diagram already gives us two measurements that are going to be important for the actual predictions. First, the size of the container is going to give us the maximum wavelength that we are going to be able to see in the experiment. And the width of the laser, it's going to tell us the minimum wavelength that the experiment is going to be able to resolve. This in hand turns into saying what is the minimum value and the maximum value of the wave vector that we expect to see. So, with this in hand, I took some parameters of a previous paper from the group and drew the linear dispersion relation in blue in this plot, and grabbed a usual dispersion relation that has all the terms for surface tension and is more complete on the dependence on the height of the film. And we can see that around this value of k, they start to diverge using the parameters of the experiment. However, with the observation that I made before for the minimum value of k and maximum value of k, the actual experimental range that we are interested in seeing is determined by these two vertical lines that I have here. In both of these cases, both dispersion relations agree completely. So what we are really actually interested is studying the linear regime of dispersion. So now we can compute the actual Weidmann function. These are the results that that Samin Tajik, present here, found already for both detector moving in a circular trajectory of radius r and detector moving along the x direction with uniform velocity. The idea is to take both response functions and subtract the contribution due to the Doppler effect. That's what this part describes. With that in hand, and assuming that the dispersion relation is monotonically growing, again, I'm not going to plug in yet the values of the third sound, the linear dispersion for the third sound modes. We find that the response function for the circular motion can be written in a mode sum structure when we can separate both the contributions from the vacuum that are in blue and the thermal contributions that I wrote in red. Formally speaking, if we were to use any kind of dispersion relation, the k plus and km are defined through a set of equations. In the case of linear dispersion, this can be found explicitly. We can do the same and leave it in an integral form for the linear motion in this case. Again, we separate the vacuum contributions and temperature, finite temperature corrections. If we have the linear dispersion case, now we leave everything in terms of the energy of the detector and the angular velocity of the probe for the circular motion. And we can leave everything in terms of the velocity in the case for the linear motion of the probe. Now, this is a point of contention, contention for me at least. If we go on and plot this for how many times I have? 6 minutes, perfect. Using the two different dispersion relations I already showed, having the height of the helium being around 100 nanometers, not a very thin film, using a radius for the circular motion of 40 micrometers and a velocity of 0.95, the velocity of propagation of the third sound waves. In this case, what we find are that the response functions in both dispersion regimes are very, very different. One is 200 times more than the other. I'm going to get to this, don't worry. I know this is telling me something is wrong. If we go to more realistic parameters, the difference is not so much, but it's 2 times the difference this time. These plots were performed with the 30 nanometer depth and a 1 millimeter radius, and considering that the laser is 0.3 millimeters wide, it's already kind of difficult to actually see a circular trajectory. What I want to point out here is that in both the linear and the modified dispersion regimes, we are going to have most of the difference between the circular motion response drawn in blue and the linear motion in orange around the zero energy case. Yeah, and this happens for both cases. But the scales already tell me there is something wrong. First, these calculations were performed using a point-like detector. If we were to take the laser and focus it to a single eight-dimensional point, that will require an infinite amount of energy. We cannot do that. As we saw, the values of the response function reaches are very different in modified and linear dispersions, and this suggests the fact that the high values of k are problematic due to the structures of the equations. This does not account, and everything I just showed does not account for the size of the laser, or the size of the sample. So if we were to take all the real values of k that we have put on the integrals, sorry, let me rephrase that. What we have done is take all the possible values of k from 0 to infinity. What we actually want is to have the values of k in the integrals that respect the container size and the laser width. So I don't know why that happened, but the other point I wanted to make is that in the superluminal regime, meaning the modified dispersion, the constant velocity of the circular probe is compared with the group velocity of the waves. It's going to be each time for growing energies, the group velocity also grows. So if the velocity of the probe is constant, what we have is that we are getting, as we increase the energy, we're getting farther and farther away from the speed of light for that value of the energy. So that also is a possibility of why we are seeing such heavy differences on the values these functions reach. So an idea is to replace the interaction model. In the Hamiltonian, we can add now another function that is dependent on position, and in the end, the idea is that it would be sensible to the wavelengths of the laser. No, I mean, sorry, of the waves in the surface of the helium, and that in turn would modify our integrals from going to 0 to infinity to respect the size constraints of the container and the width of the laser. I know at least that Jorma and one of his former PhD students, Cameron, are working on this part of the problem. The rest keeps being work to be done. And the nice thing is that doing this will keep us in the linear dispersion regime. That's what we're interested in. And yes, that would be my talk.
Okay, thank you, Felipe. And let's take it to the room for questions. Yep.
Thank you very much for really lovely talk. It's very clear. So in terms of like you're speaking about the limits of the K integral there. Also for the limits of the T integral, the time integral.
Yes.
It seems that throughout you've assumed that you're essentially in the steady state solution. You can integrate from minus infinity to infinity.
Yes, that can be attributed to giving a formal form of the switch function.
Yeah. So there would be finite time effects in the experiment.
Yeah. Yes.
Would depend on the switching function. How long does it take for the detector to thermalize? Is that an issue, or is it really quick and you don't really have to worry about it?
I don't know the response at the moment, but I know Jorma has a paper on that.
Okay.
Jorma, did you want to add to this?
Long story.
Okay, long story. Okay.
It's a full paper, so yeah, it's a long story. Yeah, waiting for Unruh.
Maybe we can keep this as a discussion for the coffee break then.
So maybe I can just quickly. One of the good things of using helium is that you can continuously interact with it, and that it can, in principle, be there for many, many hours before you have to go, because before the temperature rises and you have to cool down again. So you can, in principle, of course, interact for long times in several, trajectories, several, circular trajectories, and you want to be in a state where it's not just, where the system is in equilibrium in a way. The problem is, of course, when you interact with the system, you're also doing something to it. So you may trigger back action. This is also something that we are calculating, particularly in a finite size system. This could create problems. So one of the things is really to find out, develop models for that, also to include back actions, what we've done, finite size effects, and then to see if that's what we see in the experiment. And then it is very easy to put yourself out of that regime, by cranking up the intensity of your laser beam, which is then beyond what is easily calculated, for example. So it is something that we need to find out.
Okay, and to keep us on time, I'll close the questions on that one, and let's thank Felipe again.
There's the mic.
Check this first.
So if you press here, is it? You can put it to your color maybe. Would you like to try and put it on?
5, 6, 5, 6.
Rick, is that good? Okay, right. I was wondering. Okay, so for the last last talk of this session, we're going to have Jorma Louko talking about the back action of Unruh DeWitt detectors. Please take it away.
Thank you very much, and thanks for the organizers for this opportunity to speak. Yes, this is work done at the Nottingham Manchester Gravity Lab. So Adam Wilkinson is a PhD student at Nottingham, will be graduating next month. Leo Perry is a PhD student at Nottingham, will be having his PhD viva next month. Then there's me, and then there's Bill Unruh, who needs no introduction, a frequent collaborator, visitor to the Gravity Lab. And in this project, it was Bill who kept us on the straight and narrow whenever we found ourselves barking up the wrong tree. So, topic here. This has to do with the acceleration effects in relativistic quantum field theory, specifically when an Unruh DeWitt detector, about which we've heard, reacts on the ambient quantum field. What is the back action? And the keywords in this title here is, you are in a relativistic space-time. You should be doing it in a relativistically causal way. You should be doing it in a covariant way. How do you do perturbation theory this way when perturbation theory says that you should be doing time evolution there? This is a topic that has been around for decades, and I hope to set the stage of why it has been there for decades. But we believe to have made some progress, and I want to tell about that progress. So first, I'll briefly recall some facts about the Unruh effect, and the aspect that we are interested in is the back action on the ambient quantum field, and in the relativistic context, this is characterized by the stress energy tensor of the field. And then I'll be telling about the particular system that we are talking about. Will be in the relativistic setting, not in the laboratory setting for this talk, in a relativistic spacetime setting. And we're working with a poor man's electromagnetic field and the detector that we've heard about. And then we'll be doing the evolution in a space-time covariant way. So that's sort of a theory part of what's new here. And then I'll do applications to, dare I say, my favorite space-time. And my favorite trajectories there, inertial and uniformly linearly accelerated. And I'll show some plots there with arguably some artistic value even. Okay. Any questions at this point? Okay. So we've heard about the Unruh effect. It's a well-established prediction in relativistic quantum field theory. In its standard form says you take Minkowski vacuum, you take uniformly linearly accelerated observer, and under certain reasonable assumptions, they will experience the Minkowski vacuum as a thermal state in a temperature proportional to the acceleration. And this is a prediction that has observable meaning. If you have some local quanta that couple to your ambient field, you can see this by the excitations and de-excitations in your system, in terms of transition rates up and transitions rate down. So my favorite way to think about this is that I am in my spaceship, and on the shelf there in the cabin of the spaceship, I have different jars of atoms. There's a jar with antimony, arsenic, aluminum, selenium, and so on. And once in a while, I look in each of those jars, and so I see which fraction of those atoms are in their ground state, which fraction of the atoms are in their excited states. And the Unruh effect, the prediction says that this depends on how I'm using the engines of my spaceship. If I'm inertial, I see certain things. If I am accelerating, I see something that should be proportional to the acceleration according to this detailed balance formula. So it's a very observable kind of prediction. You can say it's a prediction with which you can cook your steak. As other peoples have alluded to date, no steaks have been cooked with the Unruh effect. When you put in the appropriate dimensionful constant, it says for 1 Kelvin you need some humongous acceleration. So in the relativistic space-time setting, this is difficult to observe. As we've heard, there is interest in doing this in analog spacetimes, okay? And the selling point there is that this c here, it's no longer the speed of light in vacuum, it's the speed of sound or phonons or whatever in the system you have in mind, and that's much less, and that brings the temperature up and gives prospects. And that was a topic for a number of other talks. In this talk, I'll stay in relativistic spacetime, and I'll now think about the back action on the field. I mean, this has to do what happens in the jar of antimony atoms and so on. We'd now like to ask, how does the ambient quantum field react to this fact that something has happened in that jar of antimony atoms? This topic has been around for some time. It has a significant literature. I will mention here my favorite paper from that literature. So this comes from the early 80s. What happens when an accelerating observer detects a Rindler particle? What happens to that ambient field? Okay. Authors Unruh and Wald. If you do an online search for this paper by the authors Unruh and Wald, I recommend that you turn autocorrect off. My autocorrect turned it into unruly and wild. Okay, but you can find the paper. You can find the paper. So what happens? The paper found that when this detector gets excited, then that detector excitation is accompanied by emission of a particle of some sort into the ambient quantum field. So if you have something local in an excited state and there's a spontaneous downward transition, that's accompanied by emission of a quantum. That should not be a surprise to any of us. I mean, the lights in this room operate on that principle. You excite the atoms there, well, ions probably. You excite them with the with electricity, and then there's a spontaneous downward transition and light comes out. This paper says that the same thing happens even if you have an ambient Minkowski vacuum, but this accelerating observer, there is a spontaneous emission of a particle of a certain kind into the space-time. So why is there still this humongous literature and discussion going on? Well, it has to do with this notion, what exactly does emission of a particle mean? And this is a good moment to remember that quantum field theory is not a theory of particles. Quantum field theory is a theory of fields. I mean, the clue is in the name. Fields sometimes like to localize. The electron field quite regularly localizes into electrons, and it's useful to think of them that way. The electromagnetic field, it often localizes into photons, and it's often useful to think of it that way. Like today, if you go out and decide, should I buy some sunscreen, then photon is the relevant concept here. But when you think of emission of that sort and you try to analyze where does that emission really go, particle is not the right concept. You need to think in terms of local observer of the fields. And so there's long history and ongoing discussion. I mentioned here one of my recent favorite references on how you do this in terms of localized observables. So you need to think of it in terms of fields. And that's what I'll be doing today. So I'll be looking at the stress energy tensor that this accelerated quantum system makes happen in the field. And I will not even look in the jar of antimony atoms. I will just look at what happens around it. I will never open that jar. I will not look inside there. And the key theoretic concept is that you want to do it in a relativistically covariant way, and you want to be sure you do it causally so that what you predict at that space-time point x, it only knows about the causal past of that space-time point x. Okay. And technical note, if you've worked with the Unruh DeWitt detectors and thought about their excitations, de-excitations, for example, the way Felipe did, then first order perturbation theory is okay. Here, if you do it this way, second order is necessary. So, system, right. Globally hyperbolic space. Well, let's say, if you are not fancy, if you are not keen on this jargon, just think of Minkowski space, Minkowski vacuum. More generally, this works in a globally hyperbolic spacetime, so time evolution is predictable. And we'll work with Pullman's electromagnetic field, that is a real scalar field, and a state that is, well, it's sufficiently like Minkowski vacuum that we haven't put in there any pathologies or any excitations to begin with. It's kind of a vacuum-like state like that. And as the quantum system, we'll use the textbook Unruh DeWitt detector, okay, Unruh DeWitt, point-like two-level system prepared initially in one of the energy eigenstates. And it's moving on a world line, prescribed world line through the space-time. We are not asking who keeps the detector moving. There's some friendly neighborhood external agent who keeps pushing the detector. We'll just take that world line as given. At this point, you might start getting scary. Point-like, quantum fields don't like point-like things, so you might be worried that is something going to go wrong here. Amazingly, no. This is just on the knife's edge of where point-like detector is still okay. There are settings where point-like things bring problems, but this is just at the knife's edge, on the right side of that edge.
But is the result changing if it's not point-like?
Then it's a new game. We are dealing with a point-like detector. Non-point-like detector is a new game. And that brings all kinds of issues about, if it's not point-like, is there a causality at some level? I mean, this Fuster-Verch net formalism that I mentioned, it makes the case that if you... let me not go on the tangent. Okay, it's a big story. If you want it not to be point-like, there are new questions that arise. Here they don't. And I'm just on the safe side of the knife's edge. So, interaction. This is the interaction that we can look up in the standard literature, so goes back to Unruh DeWitt. So, interacting linearly with the quantum field at the location at the detector. We are doing perturbation theory in some coupling constant, then there's some way to turn the interaction on and off. And here is the raising operator, the lowering operator, and there are those things associated with the gap. This is the sort of standard two-level system coupling that you would write down. And it's modeled on the electromagnetic dipole interaction and so on. So this is very much a standard thing. And you would call this the monopole moment operator that we saw on some of Felipe's overheads. So that's the system. What you want now is the stress energy tensor to order c squared. If you try to go beyond c squared, then the point-like thing would start hitting you. To order c squared, we're just about okay. So isn't this a straightforward thing? You just do time-dependent perturbation theory and that you know and love. You learn about it in second year, maybe third year quantum mechanics. So, right, there's a time evolution operator. We're working in the interaction picture. There's the interaction Hamiltonian we just wrote down. Okay, we do it as a density matrix there. Okay, and then you expand, you do a perturbative expansion. This looks like almost like second, third year quantum mechanics time-dependent perturbation theory. Then you want this. So what's the difficulty here? The difficulty is sort of hidden over there. It's trying to stare you in the eye, and it has to do with the fact that we've got 2 points here in a relativistic space-time. And if somebody gives you those points in a relativistic space-time, there's something in those formulas that you don't know. And the thing you don't know in those formulas is, but how far do you evolve this system? In fact, I've written this here as if you were just evolving in some time parameter. It's more complicated than that when you're in space-time. You're not evolving along a world line. You're evolving among Cauchy surfaces. So if you were Newtonian, you would be doing it like this. Okay. evolution like that. If you're in Minkowski space, if you're doing special relativistic things, well, you could certainly do it like that, but you could equally well do it like this too. Okay, you could equally well do it like this too, and those tau f's that you have in the formula, they would differ. So which one do you choose? And if you're in a curved space-time or in flat space-time with curved foliation, then you need some better gear to demonstrate, but you could have some more complicated evolution. So there's no tau f in this picture. What do you do? So, the tau f in those formulas, there are 3 steps that tell you what to do. So first you say that you take tau f somewhere here that's space-like separated from that point. You pick it arbitrarily sometimes or somewhere over there, so technically on some Cauchy surface and so on, but you pick it sometime over there. And then you take a closer look at the interaction Hamiltonians you had, and you see that they had commutators in them. Well, what's a commutator for a scalar field? It's the difference of a retarded and advanced propagator. Then you look at the integration ranges in those formulas and say, but where you integrate that commutator, it reduces to the retarded propagator like that. So in all of your formulas, the commutator you can replace by the retarded propagator. And after that, you look at your formulas again and you realize tau f drops out entirely. For all that you care, you can set it to infinity in your formulas, and it's the retarded propagator that takes care of causality. Basically, it takes care of the things only doing interactions down here. Okay, let me get rid of that. Okay. One more fine point. So this is the picture that goes with one space-time point. Remember, we wanted something else. We wanted a 2-point function. So you really need to think of a case where there's not just an x, but also an x prime here, and talk through the tau f like that. But it can be done. So this takes care of the causality. And outcome is, to the second order, the second order contribution, you can write a formula where you have the retarded propagator that takes care of the causality bits. Then there's the Whiteman function there that knows about the initial state in which you've prepared the field. For technical reasons, this formula might scream if the points are not time-like separated, but for our purposes, it's okay to take them time-like separated. And for close enough points, this is now fine. So now you've got the 2-point function, and so what do you do with the 2-point function? You wanted the stress energy tensor. There is standard literature on this. You operate on it with a certain differential operator. You subtract geometric terms to renormalize it. At the end, you take x, go to x prime, and that gives you the second order contribution to the stress energy tensor. Are we done? We're not done. Subtract geometric terms. Okay, in a general space-time, that's a complicated thing. But suppose you're in Minkowski space, then you know exactly what those geometric terms are. They are the Minkowski bit. And in fact, this bit doesn't need any renormalization. But this bit is tricky. Okay, and this is a good moment to remember that the Whiteman function of a field, it's not really a function. It's a distribution. There are secret I epsilons hiding in these formulas. Further, when you take x equals x prime, then the limits of integration pile up in a place where you have a singularity. And so just by staring at that formula and you try setting x equals x prime, no. It needs to be done in a more careful way. You can start from there, but what it means to take x to x prime, that takes some work. And what we did is, here we went to 3 + 1 Minkowski, and we took a massless field. So significant amount of work in taking that limit, limits under the integral and so on. I'll just show what the answer is. Stress energy tensor looks like that, where this I thing is this lovely formula here. It knows about the energy gap, appears in several places, and then there are these several functions here which all have an obvious geometric meaning, right? The switching appears there someplace. And then in the formula you saw this tau minus thing. The tau minus is over there where this path crosses the past light cone. This formula, it only knows about what happens in the past. So you now give your favorite trajectory in Minkowski space, 3-position Minkowski space, plug it in that formula, and you know what the stress energy tensor is. And here I want to show my two favorite examples of trajectories. How am I doing with time? Oh, thank you. Right, so first example, my very favorite trajectory in Minkowski space, inertial detector. So in Minkowski coordinates sitting at the origin, and Minkowski time is the proper time. And I'm now taking the switching to happen in the asymptotic past. If you still remember several overheads back, you might remember that to begin with, I took the switching function, the thing that tells how you switch the interaction on and off, I took it to be smooth and of compact support. And that guarantees that in my workings everything is fine. Now when I have that formula, I can ask, does anything scream if I let the switch on go to minus infinity? Absolutely nothing screams. I can take that limit over there, and this is what comes out. So, spherically symmetric system, I look at the energy density and the energy flux. So TTT, energy density, so T is the Minkowski time. This is the energy density. So this is the radial coordinate. There's where the detector is. Then you go away from the detector. And there's a color plot of what happens. There's more energy density down here at negative E. There's less energy density up here at positive E. E was the gap. And the notation is such that when E is positive, then the detector was prepared in its ground state. When E is negative, then the detector was prepared in its excited state. So if the detector was initially excited, then there's a lot of energy density that has come out. If the detector was initially in its ground state, not so much, but still some. Okay? And you can do fall of estimates over there. Right. So one observation is that this is strictly positive even if the detector was initially prepared in its ground state. It's not very large, but it's strictly positive. Now you might be puzzled by this. We certainly were puzzled by this. For if you were to if you were to look at the detector, and you were to look at the transition rate in the limit of long coupling, then the textbook wisdom says that if the detector is initially in ground state, there's no transition rate upwards. There are no spontaneous upward transitions. There are spontaneous downward transitions, so you would expect something here. You might have expected 0 up there. Now we were puzzled by this, and Leo Parry insisted that we think it through from the detector point of view. Well, we have in the paper an appendix for which the margins of this talk are too narrow. But the point is, it has to do with this distinction between transition probability and transition rate. It is true that in the long time limit, excitation rate is 0. But if you are thinking of the excitation probability over a long time, then it's a different story. And that accounts for you having something non-zero over there.
So on the right-hand side says there's no energy flux from the detector to the space-time.
Yeah. Yeah. So that was the energy density. Energy flux. There's no flux over there. Okay. So that is kind of more like what you would expect. There is an energy flux over there, and you can in fact get a nice formula, and it says that that energy flux from the detector, it's exactly what you would expect. There's the transition rate of the detector times the gap times the area. This exactly balances the flux, the de-excitations that you get if you were looking at the detector. So, well, my favorite trajectory, but not a particularly excited one. I should mention that, so there was one online meeting with Leo and Adam. I was at home and I had one of those pictures on the screen. And Jennifer, my wife, walked in the room and she looked at the screen and she mentioned the name of an American artist. So have a look at those and those. So action replay, science, art. Surely some of you know, recognize who this is. Yes. It is Mark Rothko, very good. There are lots of his stuff at Tate Modern in London. Okay, so art imitates life. Although I need to admit that I've slightly cheated on this one. So let's look again at this. Okay. On this one, I've displayed it here upside down. But I'm in good company. Apparently there's a long history of Rothko's painting hanging in galleries upside down because the curators can't tell the difference. Okay, so the interesting trajectory. Is this to the 30-minute mark or? 30 minutes, yeah. Okay, I can see there's a hand there.
Could I just ask a quick question on the previous slide so that I understand that?
This?
So I'm just trying to understand the energy density plot. So is this a steady state?
It is a steady state. So you started with a interaction profile that was of finite length, but then you took the limit where it was unit and the switch off was turned to infinite past. Okay. You are, when you do that, you are afraid that something goes wrong because of the infinite interaction time. And it sort of does. Here, there's a divergence. There's a non-integrable divergence. If you wanted to integrate the total energy on a spatial slice, the total energy would diverge over there. So over there, you don't really trust this thing anymore, but over there, I would trust it.
So I don't worry about the detector de-exciting at any point. That's that it's like. So I mean, imagine it's in a excited state in the distant past, so, and I just wait forever and.
Right. So let me make a comment on that second-order perturbation theory thing.
Yeah.
So the calculation is set up so that you don't look in the jar. You don't ask whether the detector gets excited or not. You never measure the detector. So that means that if you were to think of it in terms of excitations or de-excitations, what contributes to this process is something where there is an excitation, or well, there is a transition, and then there's another process that contributes where there's two transitions, up and down. Both of them contribute, and both of them are included here. If you were to condition this system on a transition, then the answer would be different, and you would need to think about the causality in a different way. For where would you measure the detector? Okay. But here I'm not measuring the detector.
Okay, thanks.
So if you have a detector and it would be excited, then the process would end because it got detected, no? I mean, so this way you can have like one up and down because all of them you're summing over in a way.
Yeah, so it's second order perturbation theory, so you can have up and down, but not more than that, then it would be higher order perturbation theory. Now I'm in the danger of never making it to the interesting trajectory.
Yeah, I'm going to stop us on the questions for the sake of continuing the talk, but of course the talk allowed for questions. This was sort of questions too, so please carry on.
Okay, so let me show a few pictures of the interesting trajectory. So this is the Rindler trajectory, uniformly linearly accelerated. Here's a space-time picture. There it is. Okay, so similar questions. Switch on, similarly pushed to infinity. So there's a space-time picture of the trajectory. Let's look at a space-time picture of the energy density and the flux. Right, switched on the asymptotic past. So energy density in the Minkowski frame, so TTT, left-hand side the energy density. You can see where the detector trajectory is. So divergent energy density there, but that's what we expect. And this tells you what's happening. So over here it's positive. Over there there's a bit where it's negative. So for when the detector was initially in its ground state, then there's something negative, something negative, something negative in a very small region over there. Okay. Diverging near the detector. And so it's negative all over the horizon. In fact, it has a mild divergence over the horizon. It also goes negative in the far future over there, and you can write a formula for that curve if you like. So TTT, it has more structure. You expect a mild divergence on that horizon because the thing has been working since minus infinity. There are things, and it's asymptotically null at past infinity. So things will pile up on that horizon, so you expect singularities there, and you do see those singularities there. So TTT, nice. Flux, well, that's a mess. And it's a mess because it's not a stationary situation in Minkowski frame. Right. But there's a way to think about this in that right Rindler quadrant where the system is stationary with respect to boost, the Rindler time translations. And if you do that, then in that picture the plots look like this. There's the detector, so that is the spatial coordinate. This is not a space-time picture now, it's just the spatial coordinate. Everything is time translation invariant. But there is the negativity near the Rindler horizon if the detector was initially in its ground state. For energy flux, right, negative near Rindler horizon. Now that again looks like a piece of art, but what it says is that there's an energy flux from detector when E was negative. That is, if the detector was initially in its excited state, there's a flux towards the detector if the detector was initially in its ground state. And this is what you would think if you think of the detector excitations, even though we don't measure them. And you can make it better than that if you go off the plane of the detector's trajectory. Here's a plot where the detector's trajectory is that plane, and I've plotted one dimension that is off the trajectory. There's the detector, and here is the flux. This is in the case where the detector was initially in its ground state. The flux is moving to the detector. You can write an asymptotic formula for it. And this flux, it exactly accounts for the energy in the detector's transitions. Even though we don't ask who is accelerating the detector, the flux in the field, it's exactly responsible for the upwards and downwards transitions in the detector. And that's where I really should, right, that was the point. And that's where I can stop. So back action in terms of a relativistic space-time T mu nu can be done in a causal covariant way. And for me, the biggest selling point here was that the energy flux, it matches what you'd expect from the detector excitations and de-excitations, even when you don't measure them. And this was relativistic space-time. we'd like to do analog space-time, and here's a set of questions that you would like to answer there, and I sincerely hope that over the coming years we will. Thank you very much. I will stop here.
Okay, now let's turn to more questions in the room. Yeah, Samin?
I have a question regarding this positive and negative part. I was wondering if you can think of it as what Bill's initial paper also explains as a two-mode squeeze state, in a way that when you have your detector, which is in ground state, it will get excited by absorbing a negative energy, and it will get excited, and then it will decay and release another photon, which is in positive energy state, into a Minkowski, so from a Rindler to Minkowski, and then you have these two modes being in squeeze state or entangled photons. And then this is how we can also look at the energy density and energy flux of the detector, but also from the point of view of two particles that are in two-mode squeeze state.
Is compatible with that and going in the same direction. So I'll say again that we've deliberately not described the back action in terms of field quanta that get emitted. We've described it in terms of the local quantity, the renormalized expectation value of the stress energy density. And what we find, particularly with the energy flux here, it is compatible with what you were describing.
Okay, yeah, Silke?
Well, I think one of the things that would be very exciting to do is to say, well, if you make the measurement, you change the field, but the measurement is not taking part when you couple the field, is when you actually measure or evaluate the detector physics. In other words, if you measure, you have a detector that interacts with the field. If you haven't measured the particle, if you haven't looked at the detector, if it's excited or de-excited, that would mean that the measurement took no place, no?
So, two comments. First comment is part of this question mark, needs some thought. The second comment is, if you start also measuring the detector someplace, then you need to ask, how is that measurement related to this notion of expectation value over there? And the best framework that I know about for addressing that would be the Fuster-Verch network framework. Might not happen in the next year, but maybe in the next couple of years.
I mean, it's really one of the competing effects, of course, because all of this is derived in the assumption that you can neglect back action, because you have this field, it's just open, you can just, whatever you do is infinite, scalar field provided, there are no boundaries, no containment of whatever energy you're putting in there. So, and you need to interact with the field for a certain amount of time, and also then somehow you have to figure out how you implement a measurement process where you have enough time to say with or without actually looking at the detector, and there needs to be a time scale somehow. But if there is a window, maybe you could show that the interaction takes care retrospectively in a way, because it's always interacting, but if you don't know what the detector is in an excited or de-excited state, that hasn't happened. So the moment you measure, it happens, you measure here, and that's inject something in the field.
When I was preparing this overhead, I was debating whether I should put more question marks over there, and maybe I should have done so.
That's really interesting. It's conceptual, right? You're testing something about the paradox of this whole encounter, and you can do this in a tabletop experiment.
Okay, formally we are out of time, but if you would like to ask a question, because the next session is the next 30 minutes is a coffee break. If you'd like to keep everyone waiting because your question is important, please go ahead. Yeah, I didn't think so. Okay, so let's thank Jorma again.
Thank you.
And we'll reconvene at 3:30.
Okay, welcome back, everyone. So for the first talk of the last session, we have Bill Unruh talking about black holes, entropy containers, or creators.
Well, it's been just over 50 years that when Stephen Hawking argued that black holes, rather than being black, emitted radiation. Temperature proportional to 1 over the mass. And since the entropy is clearly since the energy is clearly mc squared, you just use TdS equals dE to calculate the entropy. And you get that the entropy should be equal to 1/4 of the surface area of the black hole. This is interesting because that was the surface area of the black hole was also what Stephen Hawking argued must increase as long as the energy flow into the black hole was positive. So as long as you had positive energy, that should increase that thing, which is what we think about as entropy. And that led to the generalized law of thermodynamics for a black hole, where the black hole has that entropy, etc. What's important here is that calculation of the entropy of the black hole is calculated by integrating the total energy, the total entropy that was emitted by the black hole over its lifetime. It's not a derivation of the black hole having an entropy like that. But the dominant belief has always been, well, especially since this is related to the surface area of the black hole, that the black hole has inside of it an entropy that's that's equal to this 1/4 of the surface area. But that then led to the question, where in the world is that entropy inside the black hole? What is it that carries that entropy? It has to be inside or on the surface of the black hole. After all, where else could it be? That's the black hole. And people have searched for various things, holographic principles, string D-branes, puncturing the horizon, etc. The information paradox is all part of this. And the primary analogy that people basically used was that a black hole is like a lump of coal. You have a lump of coal which is at absolute zero. You take out your favorite laser, shine it on that lump of coal, it absorbs the energy from that laser. And of course the laser is giving highly coherent light, but once it gets into that lump of coal, all the atoms jiggle around and crash out with each other, producing a highly entangled state between all of the atoms inside the lump of coal from the energy inside that laser. And then you stop shining a laser on it, and the lump of coal gradually radiates. It radiates energy, but at the same time it also radiates entropy. And after a while, for a solar mass black hole, the estimate is 10 to the 53rd times the age of the universe. So this is a very, 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 very slow emission of entropy. It finally cools down to zero. In the case of the black hole, that would be zero mass and zero entropy. But I've always been bothered by this. Entropy in pieces of coal and so forth, I understand what's going on there. There's all this very high nonlinearity, crashes of atoms with each other, which are highly nonlinear. And yet when you look at Hawking's derivation, it was purely done using quantum field theory, moreover, linear quantum field theory. There was no nonlinearity in his calculation. So where in the world is this entropy coming from? And after all, the simplest way of thinking about the formation of a black hole is that the radiation from a laser, which forms the black hole, let us say, it goes in across the horizon and falls off the edge of the universe at the singularity at r equals 0. That's a completely consistent picture. It leaves behind its gravitational field. The singularity becomes stronger as the laser light goes into it. But there's no nonlinear mixing. There's no storage container in there. Anything that goes into a black hole disappears off the edge of the universe, and you never see it again. And nothing inside that container can ever get out across the horizon. So where is this entropy if a black hole is supposed to have entropy? I've always been bothered by this. They go ahead, and one of the reasons for introducing string theory was, in fact, to try and explain the entropy of black holes. Oh, I wasn't supposed to talk about a lot of this. Anyway, and there's another number of cases throughout my life in which I've been bothered like this, and I turned out to be valid bothering. For example, Bohr-Einstein debate on delta E, delta T, where Einstein claimed to have a contradiction to that, where he had a box, he weighed the box to find out how much energy was in there. He had a little shutter operated by a timer in the box, which opened it and let out some radiation, so he could measure exactly how much radiation escaped. And by the clock, he knew exactly when it was emitted. And poor Bohr ran away that night and spent the whole night awake trying to figure out a way around this, and found a particularly effective argument where he said, general relativity, yes. You can weigh energy in general relativity, but it also says the clocks go at a different rate. And therefore, by weighing that box, you don't know what time exactly the stuff came out, and if you do the calculation, you get exactly delta E, delta T. However, that would seem to say that in order for quantum mechanics to be consistent, general relativity has to be true. But that's too much. Furthermore, you shouldn't have to introduce brand new theories, general relativity in that case, in order to explain some physics. Classical physics, for example, might be wrong, but it's not self-inconsistent, which is what this is implying, that you have to bring in new ideas. Bekenstein did the same kind of thing with black holes. So, is there some better way of thinking about the entropy of black holes? The answer is, I will argue, yes, amplifiers. Back in 1974, when I started at the University of British Columbia, I was taking over a professor who had just died. I looked through his papers, and I happened to come across this paper by Haus and Müller about amplifiers, which argued that any amplifier also has to produce radiation, noise. They couldn't argue that it was thermal, but everybody knows that amplifiers produce thermal noise. And this turned out to be very important from the work I did on LIGO and how the noise in LIGO and how accurately you could use LIGO in order to measure gravitational waves and so forth. Part of this turned out to be something that I didn't understand until at least a number of years later, and that is two-mode squeeze states.
So let me give you the bare outline of what one means by a two-mode squeeze state. We have two harmonic oscillators. And one of the oscillators has annihilation operators A, and the other has annihilation operators B. They commute with each other because these are two separate harmonic oscillators. And this system goes ahead and develops. And after a time, you look at it and you discover that A and B, that the annihilation, the natural annihilation operators are now C and D, where, as these are harmonic oscillators, they're a linear system, they must depend on A and B. If you do the commutation relationships between C and D and A and B, etc., and C dagger and D dagger, etc., you find that generically you get that C has got to be equal to cosh R times A plus sinh R times B dagger. And similarly, D has to be cosh R times B plus sinh R times A dagger. In doing this, you also have to sometimes absorb phases into A and B or C and D. This is called the Bogoliubov transformation if you look in condensed matter physics, for example, or even quantum field theory. And that usually arises in those theories because of time-dependent development, that the system is not time-independent, but is time-dependent. Now, when you start off, the vacuum state is the vacuum state of A and B. And that 0, 0 here is the vacuum state of A and B, that A on that and B on that is equal to 0. The first one is A, the second one is B. After this interaction, of course, the annihilation operators, as I said, in the Heisenberg representation, remember in the Heisenberg representation, states do not change, the operators change. That's why these operators the later operators are functions of the earlier ones. But the vacuum state, according to these C and D operators, is going to be some other state, which is annihilated by C and D. Well, here's C and D, and the operator and the state that's annihilated by that, there's a B dagger in there. It's not the same as the state of A and B, as the ground state or the vacuum state for A and B. It's some other state. And in fact, we can write it as 0, 0, the original vacuum state, is equal to the final vacuum state times this operator. Whoops, didn't want to do that. This operator times tanh R, before you had cosh and sinh. Here you get the tangent there. And we can expand this in this form, and eventually I can get this. I find that this is just equal to e to the something or other, depending on R. R is what's called the squeezing operator, the two-mode squeezing operator, times n, the number of particles, times the state which has the equal number of particles in the C and in the D state. If I now only look at the C output, I never look at D, then this is just a thermal density matrix, where this term up in this term here is the energy divided by the temperature. Now, generically, what one finds when one does this is that that temperature done this way actually is a function of the energy as well. So that each set of modes that act like this has a different temperature. Let's produce a simple model of an amplifier. So I've got two fields, phi and psi. They're input fields and output fields. They interact only at x equals 0. This is a 1 plus 1 dimensional system. They interact at x equals 0 via a harmonic oscillator. Well, this is a harmonic oscillator which has 0 frequency, i.e. is just a free particle. The important thing here is we notice that the Lagrangian density for the psi field has the opposite time sign for the phi field. So the psi field actually has negative energy. The vacuum state for the psi field is a maximum energy, 0. And as you excite that, it gets less and less energy. And for the harmonic oscillator, that goes all the way down to minus infinity. Now, when you're taught quantum field theory, your instructor always stands in front of you trembling in fear and saying, never, 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 never do you have negative energy. This thing is completely unstable and it's going to destroy everything. They're fake. Sometimes it's useful to use them, but don't do it. That's just wrong. So here we have a Lagrangian. You say, is this unstable? The answer is, it can be. If mu is bigger than epsilon, then this system just goes unstable, exponentially increases, and you don't like it. But if mu squared is less than epsilon squared, this is a perfectly stable system. Furthermore, we notice from the oscillator analysis earlier for a two-mode squeeze state that C had a cosh R times A. Cosh R is always bigger than 1. So stuff that came in A goes out in C bigger. It's an amplifier. So this is a model of an amplifier. Now, you worry about this negative energy going down to minus infinity. Well, we all know that if you take spin 1/2 systems, a finite number of spin 1/2 systems, put them all in their excited state, the highest energy state, that will act exactly as if it were a harmonic oscillator near its vacuum. As you get farther away from the vacuum, in other words, the energy goes lower and lower, it starts deviating from harmonic oscillator, etc., and finally gets the lowest energy way down here somewhere. But in fact, you can analyze a laser like this. As we all know, to run a laser, one needs this energy inversion, i.e. put most of the electrons up into excited states. And that's doing the same kind of thing as these negative energy harmonic oscillator that I have here. So one can go ahead and solve this problem exactly. I always like problems that I can solve exactly, because I never trust my ability to recognize whether or not my approximation is a good approximation or not. So one can go ahead, I've simplified this, the field comes in, oscillator is sitting at x equals 0. Just behind x equals 0, I put a mirror. The mirror is a Neumann boundary condition mirror, bounces the wave back out to infinity, and so the fields come in and then bounce out to infinity. And both of them, they're separate fields, so they can both ride on the same x rail. Or if you want, you could have one coming down y and the other x or whatever. And as I said, you can calculate it exactly. And what comes out is a two-mode squeeze state. The phi and the psi fields, every mode with a frequency omega, turns out to be part of a two-mode squeeze state. And if, for example, you don't look at psi, for example, in most amplifiers like the one you have in your living room, you take psi, that psi field, and throw it away into a resistor to heat up your room. Okay. But when you look at this two-mode squeeze state, you find that it's a thermal state, as I mentioned before. So this amplifier, when you feed in the vacuum, in that mode that you're looking at, it feeds out a stream of entropy. In that case, the temperature tends to depend on the energy, the frequency that comes out. For the black hole, it doesn't. But this thing is producing entropy. Where's that entropy? There's no entropy inside the amplifier. It's not that the amplifier is slowly leaking out entropy that's somehow been put in there. It's just got this oscillator sitting in there. That's all the amplifier is, that couples the two fields together. So this entropy stream comes out with nothing inside to produce it. Furthermore, this is a completely linear system. That's why I could solve it. The fields, the harmonic oscillator, or the free particle, are perfectly linear system, and it's producing this entropy pouring out into your living room as on your records while you play them. That's a black hole. So let me try and look at black holes. I'm going to take a very simple model of a black hole. Two flat spacetimes. So I take a 1 + 1 dimensional system, and I take, a flat sheet of paper. On the one sheet of paper, I cut out a hyperbola. On the other sheet of paper, I just cut the bottom as a straight line. And I fit it like this. I fit these two pieces together. So this is a flat space-time in here. This is a flat space-time in here. And they meet along this curve, which to this side looks like an accelerated path that Jorma showed us earlier. And on this side, that same junction looks exactly like a straight line. As you get to infinity, as you go out here, this system looks as though it's flat space-time, just as a black hole looks like flat space-time when you get far away from it. Inside, it looks like a Rindler space-time, which is what a black hole looks like near the horizon. Of course, on this junction, we have a delta function for the curvature. So this is a black hole with a delta function. All of the curvature in the black hole has been squeezed down into that one line. And everything on the other side of that is flat. I know how to do quantum field theory in flat space-time. So for example, if I look at the outgoing radiation, comes out of the past horizon of this Rindler space-time or of a black hole, and I make that the vacuum state. Well, I know what the stress energy tensor is of a flat space-time, a regularized stress energy tensor. It's 0. So the stress energy tensor of the outgoing radiation in this region here is 0. There's nothing coming out of the past horizon of this toy black hole. If I go up here and I look at the radiation coming in, I'm going to make that equal to 0. Now this is the so-called U vacuum that was discussed back when Hawking did his stuff. And it's a good model of black hole evaporation. So this radiation coming out of here, once it gets into this flat space-time, has energy and momentum and is flowing out towards infinity. That's Hawking radiation. This stuff coming in is the vacuum state, incoming vacuum state. So there's no stress energy tensor here. But as you cross that horizon, you find that the stress energy tensor in this region flowing into the future horizon is not zero, and in fact the stress energy tensor is negative. It pours negative energy into the black hole. Well, we know that's what happens in the Hawking system. In the Hawking system, you get energy flowing out to infinity, positive energy, that's the Hawking radiation. But in order to conserve energy, you get negative energy flowing into the future horizon of the black hole. Negative energy flowing into a horizon makes the horizon smaller. You know, Hawking's theorem was that if it was positive, it would always increase the horizon. If it's negative, it decreases the horizon. So this acts exactly the way in which you would expect a black hole to behave. It's, however, that's what I've said already. We ask, how in the world can this happen? Well, this is what I did in that paper 50 years ago, Notes on Black Hole Evaporation. Let's look in Minkowski space. The modes, the U modes, U is the stuff that's outflowing, null radiation that's going out. The U modes have its usual quantization modes goes e to the I omega times capital U. The square root of 2 pi omega is because of two-dimensional space, and it's the normalization factor, the continuum normalization. Yes?
2 minutes before questions. I forgot to start.
Thank you. 3 minutes, but anyway. What you find is that analyticity tells you that when you look at it in terms of the Rindler null modes, the analyticity is such that it produces radiation with positive norm or positive, annihilation operators coming out, but there's negative norm on the other side of the horizon. So you get this two-mode squeeze state occurring right at the horizon. And those A's and B's, one of those A's and B's, one of the B, for example, is on the other side of the horizon. You'll never see it because you don't see anything inside the horizon. Coming out, you see all this positive radiation. Let's not do that. This is repeating what I just said very quickly. Ralph Schutzhuld and I, back about 5 years ago, 2 years ago, wrote a paper in which we used the regularization in 1+1 dimension, and Davies, Fulling, and I had done that back in 1974. And what we found was exactly what I've just said, that in the Hartle-Hawking state, you get positive energy coming in and positive energy going out from not from the horizon, but this is for that curvature singularity. In the Bowler state, you get negative energy coming out of the black hole and negative energy flowing back into the black hole. In the U state, you get positive energy going out to infinity, Hawking radiation, and negative energy going inside, shrinking the horizon. And this is just doing it this is in TR coordinates, these are in XY coordinates. So what we find is that what happens in the black hole is that you get this two-mode squeeze state being produced near the horizon, That two-mode squeeze state has some stuff inside, which you'll never see, and some stuff outside. The stuff outside looks like Hawking radiation. The stuff inside, well, you never see it. Okay, I've gotten to 0. So there's various speculations that I can talk about, but I won't here. Whoops. We can also extend this to 4 dimensions, at least with some hand waving. So the conclusion is black holes create outgoing entropy. They don't contain it, and that slowly leaks out. They're constantly containing it, and if you add up all of the entropy that flows out, it's just equal to what we call the entropy of the black hole. But you've got to trace that out over 10 to the 58 ages of the universe, because that's how long it takes for the radiation to all get out. And I think this is completely linear. You know, there's nothing nonlinear, there's no mixing or anything that's going on here. And the origin of the radiation is also what's one of the most surprising things. It's not inside or on the horizon of the black hole. It's in the curvature outside the black hole. It's that curvature that causes what seemed to be the vacuum state near the horizon to turn into a thermal state out near infinity. So it's a very different view of what's going on in black hole evaporation. Thank you.
Thank you very much for a great talk. We have time for questions.
Thanks for the talk, Bill. It's a very nice model. Especially enjoyed a lot the model with the negative energy psi and the oscillator there, right? But going back to that analogy, if I only have access to the phi field, right? If I only have access to that one, I would say that the joint system of both the psi field with negative energy and the Q are like whatever is producing the entropy on the field side, on the field phi, right? So
it's the entanglement between those two. But that's true of all entropy. Remember that the entropy in the lump of coal comes about, you got pure state coming in, as people keep saying, what comes out eventually has to be a pure state, right? That's what quantum mechanics tells us. But it's not, because the stuff inside got so scrambled up that it's impossible for us to unscramble it outside. And so in the degrees of freedom that we're capable of measuring, i.e. the radiation coming out, that's not an entangled state. That's a pure that's a mixed state, a thermal state, and that simply keeps going on until finally the whole thing disappears. You just cannot disentangle that horrible entanglement that gets produced inside the lump of coal.
But I would argue that the field inside the black hole is a part of the black hole in this sense.
Is what?
Is a part of the black hole in this sense. Like it's
what is a part of the black hole?
Whatever part of the field is inside.
Right.
Right. I would say that is the black hole system now. That is the part that we
cannot
access.
No, but that doesn't have entropy in it. That doesn't have entropy in it either. That builds up as the outside gradually, you get entropy that flows in, that is behind the horizon of the black hole, which builds up in the same way as the outgoing entropy builds up. And one can argue that what happens at the very end of time, when this thing completely evaporates, is when most of the entropy has fallen over the cliff on the inside. And that's basically the same as the entropy that came out. So in a sense, this is a system in which the entropy inside keeps getting bigger and bigger as well as the entropy outside keeps getting bigger and bigger and bigger, because they both share in this entanglement across the horizon.
Thank you.
Hi, thank you for the talk. Perhaps I've misunderstood.
I can't hear you at all, so somebody will have to translate for me.
Okay. Perhaps I've misunderstood, but if the radiation generated outside the black hole is purely thermal,
right,
and everything will fall in, will have some kind of information, then does this not pose a problem with the information paradox of if the black hole horizon is shrinking and eventually decays, the outgoing thermal radiation is purely thermal, but it can't carry the information of anything that's fallen into the black hole. So how does that preserve unitarity?
So the reason the horizon shrinks is that the vacuum state that came in from infinity, from past infinity, came in, crossed that surface, and then it looks like a thermal. It then looks like a Rindler state, and we know that the renormalized stress energy tensor in the Rindler state is negative. People did that calculation back in the 1970s already. That you know, if you have the Rindler state being only a single, it's not entangled with anything else. It's a single thing that's coming in. It's going to look like it has negative energy. So all of these pieces surprisingly all fit together. And what's crucial in all of this is that the temperature coming out is the same, or very, very gradually decreasing. It's an adiabatic process.
So
unlike the amplifier where the temperature depends quite strongly on the frequency, the black hole temperature depends very, very, very weakly on the time scale at which you look at the outgoing radiation.
Okay, so for quantum information of matter or atoms or anything that's fallen into the black hole, is that somehow encoded in the radiation that's produced?
Somebody will have to translate that. I think I know what.
So the information, the quantum information of the infalling matter throughout the lifetime of the black hole, is that not encoded then in the
information in that, you know, if you don't send in the vacuum state, if you send in junk, that just goes in and falls off the edge of the universe. It's gone.
Right. So in that sense,
there's no information preservation.
It's not unitary. Right. Okay. Thank you.
Quantum mechanics fails.
What?
Quantum.
No.
So quantum mechanics is wrong.
Look, I did the calculation I did was straightforward, everyday quantum mechanics, exactly as you were taught
quantum
in grade
mechanics
1.
As unitary evolution.
What?
So, but you just said that the evolution is not unitary.
I didn't get that.
That the evolution is not unitary.
I thought
well, it's not unitary only in the sense that photons go out this window, you will never recapture them. That causes the inside to go into a mixed state, right? So what?
But
Does that ever bother
that's
anyone?
a coarse
No,
graining
it
problem.
doesn't. Now you might say, well, I couldn't capture it, but you know, God can still put his finger on it there. Okay? One of the very few times when physicists start appealing to God in order to justify their prejudices.
I think given the interest of time, we'll thank Bill again. It was a great talk.
Thank you very much.
Ah, yes. Thank you.
Thank you. Okay. We have 15 plus 5. Yeah. And what do I plug into my laptop? Wait. Here. I don't have a... Do you want a clicker? Yeah, but what do I plug in? Do you have a USB? No, I have a HDMI? I don't have a HDMI. That's okay, there's an adapter. What's this? That's for the clicker. Okay, I can't use the clicker. Do you have a
That's fine.
We should have 2 adapters. Let me just... I can just use my laptop. You have a... No. You've got USB-C, right? Do you want to first get the presentation up? Yeah. That slot doesn't work. What doesn't work? The slot on this side. Okay, I see. I can do that if you want to put this on. Just with the fluffy plug. Oh gosh. Okay. If you... Let's see if this works. How do I... Yeah, is that right? Is that on? Yeah. Okay. And what do I press? For the next talk, we have Breagh Macpherson talking about early universe cosmology in the lab.
Hi guys, so I'm Breagh. I'm a first year PhD in the Gravity Lab, and today I'll be presenting our early universe cosmology simulator. Now that I'll be showing some work done by some other members of the group, and then I'll go on to talk about what our goals are for this project. So first, it's best to get a bit of background on cosmology. So at the start of the universe, it's believed that it begins with a rapid expansion of space, and this is led by this process is called inflation, and this is led by the slow roll of the inflaton field down its potential. Now, at the end of inflation, the universe is left cold and empty. So the question is, how do we get to the hot matter-filled universe we see today? Well, at the end of inflation, the inflaton field rolls down its potential and begins to oscillate rapidly along its minimum. And this process is called preheating. This is where the inflaton field begins to send energy to its coupled modes progressively more and more. You can see this here. This is a plot of a simulation of the momentum distribution of particles at different times. So you can see at early times for eta equals 100, just here, we have one sharp peak, and this basically means that only a handful of modes have been exponentially excited. And then as we go along to later times, eta equals 400 and eta equals 2,500, we can see that these peaks get greater and greater, and they begin to broaden and smoothen out. And this is where energy redistributes across all modes, and this process is called thermalization. Then this continues on until we can see here for eta equals 10 to the 4, where the universe reaches thermal equilibrium, and this is known as the hot Big Bang. And you can see that this also follows this power law along here. So how do we actually look at this in the lab? So you can see here we've got a setup of our shaker experiment, where we take a cylindrical disc filled with 2 immiscible fluids, think something like oil and water, and we place it on top of a vertical shaking platform. And underneath this, we put a checkerboard pattern and light this up, as you can see in this red picture here. And then we film how the interface distorts the checkerboard pattern over time. Now, from this, we use a process called Fourier transform profilometry to reconstruct how this interface has been deformed over time. So these are some images of the interface. And we can take from this a height field decomposition, which we take to be the sum of the spatial eigenfunctions, which are made up of the Bessel functions, multiplied by the amplitude of the modes for each point in time. So the interface of our system is governed by this Lagrangian here, and this is made up of 2 key parts. The first of which being the top here, which is our linear part, which basically tells us how one singular mode evolves without any interactions throughout the system. We then have our two interacting parts, which is our cubic term here and our quartic term here. And these govern the 3 and 4 wave mixing for our system. As you can see here, the interactions of the system are, the strength of them is governed by the F, the G, and the H here, which are our coupling coefficients. And we can describe these interactions using Feynman diagrams. So as you can see here, for our primary mode 4-1, 4 being the number of crests or troughs in our standing wave, when it interacts with itself, it produces an 8-2. So this would be 8 crests or troughs. Now we can also look at correlation functions, and we can measure these from our experiment. And as you can see here, we have G3 and G4, and we can see them evolving over time. Now around 25 seconds is when we predict that the primary mode has enough amplitude to scatter energy into its secondaries. And you can see here, this is when the non-linearities begin to kick in. Something else to think about here as well is that we have the G5 and the G6, and these remain negligible throughout the process, meaning that we can safely truncate our Lagrangian. Now, just look at the linear regime for a second. So the way our modes evolve through our experiment is governed by this Mathieu equation. Now, this is a very well-studied equation. It is a simple harmonic oscillator modulated by an external driving force. And this determines our flow-quint charts, which you can see here. Now, each of these crosses here are a mode in our experiment. So we can plot these on this chart, and basically the orange lines are where the instability bands are. So based on the frequency and the amplitude that we drive the shaker at, theoretically from this, we should be able to pick which mode gets excited. And you can see here that we have our primary mode 4-1 sitting in this instability band. We can then compare this with the data over here taken from our shaker, where this is the growth of the mode as it becomes excited. And we can see that it follows this checkered pattern up here as it grows. And this is the growth rate taken from the Mathieu equation until it saturates at the predicted saturation rate. Now going into the nonlinear regime, I'll take your attention to these plots over here. So first looking at some earlier times for 25 seconds. So again, this is just when the primary mode grows enough to source the secondaries. And as you can see here, this plot is quite sparse. Now this is showing the amplitude of each of the modes in the system at this time. So we can see here, this is the M4, and then these arrows show that it's sourcing an M8 and an M12. Now when we look at a slightly later time, we can see that this graph has become much more populated, meaning that energy has distributed further across many more modes. This can be further seen by this plot over here, where we have taken the envelope amplitude of the mode, and we can see how it grows across time. And we can see here that the primary mode 4-1 grows first, and then the secondaries 8-2, 12-3 begin to grow as soon as the primary mode gets up to a high enough amplitude. From here, we can also take the power spectral density at certain times. And for this plot, you can see that when the primary mode is only growing itself, the only notch above the noise detection level is this primary mode. And you can see as further and further you go along, more and more of these are becoming above the noise detection level until it reaches this power law, which is where the mode saturates. And this is key because this shows us that we have a spectral cascade, which is exactly what we're looking for when it comes to preheating. So what do we plan to do next with this? So we know the shaker can show us this process of preheating, but we'd, in an ideal world, like to have some theoretical description of what's going on. However, I'm sure as many of you know in physics, this is an open problem and it's very hard to do due to a couple key factors. Some of which being that the state is far from equilibrium, so there's no stable vacuum to expand around. It is also strongly coupled, so modes grow exponentially. And we would also like to have a real-time quantum field theory for this. However, currently no framework exists to track the quantum state evolution through a nonlinear regime. Now, some typical methods you might think to try and tackle this, one of which would be perturbation theory, where you expand around observables as a Power series in the coupling constant lambda. Now, in this you'd assume lambda to be small. However, in preheating, the occupation numbers grow exponentially, meaning that when you take lambda nk, this becomes order 1 almost immediately, therefore therefore all orders of the system would contribute equally, and it could not be truncated. Another issue with this being, additionally, there's no stable vacuum to expand around, so perturbation theory breaks down at the first instance. Now, another way you might think to get around this is lattice simulation, where you discretize the space-time and evolve the fields numerically. Now, while this does handle strong coupling, where perturbation theory breaks down, this is treated as a classical field rather than a quantum one, so we're losing information here. And if you try to fix this by introducing a path integral, this will bring in the sign problem, meaning that all the contributions would cancel out anyway. So because of this, we cannot track real-time quantum evolution, and we cannot follow the quantum state all the way to thermalization. So basically, we need a third way, a real-time non-perturbative quantum method. So where does this come from? So our idea is to use the shaker to make a theoretical description of preheating. Now, as the shaker is governed by the same Lagrangian structure as the cosmological preheating, the analog mapping is already established. It evolves in real time, so we don't have that problem anymore. And it directly accesses the nonlinear regime. Also, mode amplitudes, correlations, and cascade dynamics are all precisely measurable here. So how do we actually get a theoretical description out of this? Now, in quantum field theory and kaleidophysics, one may think to use the in-out formalism, where you look at particles coming from a faraway past and from a faraway future, and you take that overlap to get the scattering amplitude. However, this needs an initial and final state. But in our system, we don't have a final state. So we would look to use an in formalism, where we would only need an initial state, and this tracks observables evolving in time, which is the right framework for what we're looking at. Now, this in formalism can be reformulated as a path integral. So if we so this allows us to sum over all possible field trajectories. Now, the trick to this, our idea, is to split this into a free and interacting part, where the linear part, which is governed by the Maciej equation, gives a path integral that can be solved exactly. And that exact solution is the Green's function. And then on the other hand, we have the interacting part, which is the cubic and quartic terms, are then treated perturbatively on top of this exact solution. So all in all, parametric resonance is built into the propagator from the start, and we're not expanding around a static vacuum, we're expanding around a growing solution. So what have we done so far for this, as this is just a fairly new idea? We have, from the experiments, Lagrangian derived 4 equations of motion in 2 conjugate pairs for a primary mode 4 and a secondary mode 2. And these are seen here, where the left-hand side is governed by the Maciej equation, and this is only to the cubic part, by the way. And this is the source terms. And then we can, treating the cubic coupling perturbatively to the first order, we gain this integral here, where G is the Green's function built from the float-quint solutions of the Maciej equation. Now, as the Green's function is built from the Maciej equation, it already encodes the exponential growth of parametric resonance. And then, so basically, this builds resonant growth into the linear propagator and then adds interactions on top. Now, of course, this is just a classical theory at the moment, so the next steps would be to promote field amplitudes to quantum operators. And then where the shaker comes in, we'd hope to compare against the classical mode amplitude growth in the experiment to our predictions here. I went a bit fast, but this is our ideas for the shaker. Yeah.
Thank you so much, Breagh. We have some time for questions. Any questions from the audience? Let me ask you a question. So you mentioned about exciting the m=4 mode. Have you managed to excite any other modes, or
so that is something we're working on, especially because I think Maciej's after me and he's looking at some quantum information theory for this as well. So previously we have, trying to repeat this is a little bit difficult. Because of the way that the experiment's set up, we can only drive the amplitude and frequency in certain parameters, so it's a bit hard to get it to what we would like it to be. But say if we change the shape of the cylinder, or if we change the densities of the fluids, then we should be able to get it to some different modes, maybe like an 8 or something like that. Yeah.
What would the interest be? Oh, sorry, is there a question there? No, you go for it.
Thank you for the presentation. Can you explain a bit more about the in-end formalism that you were talking about? Because you said that, you didn't know the final state, so you use an in-end formalism. Can you explain a bit more about that?
So it's very new at the moment, so I don't have too much background on this, but the idea would be, I guess, to take the initial state and then get an expectation value as we go along in time, and then we'd have an observable quantum formula.
Thank you. So you mentioned that you have this, analog of a cosmological field, so undergoing preheating. Is there any control of the initial state that you can put into this preheating in this analog?
Is there any control of the
initial state that you could start reheating with?
I guess if you started filming the interface when it's already, no, I guess we would already do that. Possibly yes. I'm guessing so.
I can add to this. I mean, we did discuss a bit about it. You could use, so first of all, the problem is whatever the initial state is, our detection method is what now? 0.1 micrometer. What would you say is the resolution? Something around that, which is not enough to resolve the initial state. But one thing that we have been discussing and never done is you could use some dynamics to excite something, or you could maybe try to inject some white noise, or use some technique to say, like, look, let me raise the initial start to some level that I can measure, and then evolve that, start this as your t equals 0, and then drive some parametric resonance or some other, dynamics that would drive you into the strong nonlinear regime. So it's possible. We've never really done it, but this is something that would be nice, because you never know there's this unknown. Initially, you can't see it, which of course means you don't see the very first evolution steps, and hence this gives you some sort of guessworking what it is. And there could go something could be different than we imagine. Can't exclude it.
So let's all thank Breagh again.
Use my laptop to time me.
Oh,
Let me get my phone.
I can get my laptop. I didn't realize this was yours.
I thought about it and then forgot that I thought about it.
Right, so is this just the charger? Do you want to take the
That's
charge?
just the charger,
Or
yeah.
do you want
Yeah.
Do you have a HDMI?
Yeah.
And USB?
Yeah. Gosh, God, this is overheating more than me.
There we go. So I need to click this on.
What's that showing? Oh. Fun. That's bright.
Put that on. Okay, try to click it. Yeah. Cool.
All right.
And you got the timer. Okay.
I'll.
Are you gonna start yourself?
Yeah.
So our next speaker is Maciej Jarema. who's going to talk about measuring and manipulating information in QFT simulators.
Okay, thank you. Right, so I don't have a contents slide per se, so my contents is going to have to be my title. So I'm going to tell you a bit about what I understand as information. We've heard a lot already about QFT simulators, so I'll only be briefly touching on that, and I'll spend majority of my 15 minutes talking about how you would get information out of these systems. So starting with the information, first of all, I don't want you to forget what you think of in terms of the word information in English before I start. Usually, a mathematical physics talk will start with, yeah, this is already defined in English, we're going to define it differently, forget about that. Keep around what you think of as information. In English, we normally say when you gain information, you become less uncertain, you can make better predictions, things like this, and this is kind of a very related thing to what we would be talking about. In science, you can summarize the idea of studying information as studying how much uncertainty changes, why it changed, how you can optimize it, and what you can use it for. We're going to get to some of the measures for this in a moment. But the fun part I wanted to mention first is that in the definitions that we'll get to, you're free to choose who's doing the knowing. So this could be how much you know about a state of a system. It could be how much an environment knows about a particular momentum mode maybe. Or it could be even something more abstract, like how much does a Gaussian model know about my data. So it can this is kind of part of the reason why information theory has such a widespread in terms of data processing and all these other things. So on to some measures. First of all, just a little caveat, the information is a property of states, so we need to say what I'm considering to be a state. Classically, for now, I'm just going to take probability distributions over a phase space. I'm just summarizing here by X. And in quantum mechanics, I'm going to take the density matrix. If you like, pick your favorite quasi-probability, but we're going to take the density matrix for now. From this, you can define an entropy. It's just this equation for the Shannon, or the differential version of the Shannon entropy of a Neumann entropy. And the way to think about it, helpfully, is that it tells you how much state space is being occupied. So, like you've seen before, it's kind of linking to this idea of disorder or things like this, or you can link it to the idea of uncertainty. If you're occupying more of your state space, then you are less certain about what is going on in the system. So for this reason, it's very useful for characterizing things like thermalization, because it changes in particular ways as systems are thermalizing. It's also very useful for things like entanglement classification. The other quantity I wanted to introduce is something more akin to what we normally think of when we think of information. We have a knower and we have what they're knowing about. So we have some sort of parts A and B. Again, these could be abstract models, these could be spatial regions, this could be probes and then systems. But if you compute this quantity, what it tells you is whatever you defined A and B to be, how much correlations are there between them. And it counts all correlations, so it doesn't matter if they're quantum, distillable, classical, second, fifth order in statistical expansion. It just gives you a number of how different are those two systems A and B from being independent from each other. For that reason, it's very useful for things like correlation scaling. If you define a region, spatial region of your field, for example, as over here, and you ask how much they know about each other, you can change how large A and B is or what their shape is and ask how much they still know. Or you could define A and B, for example, as parameters of a model, and then you can play with optimizing the model using information theory. So this is just some of the measures that you can define and some fun you can have with them. One of the things that emerges a lot when you're doing these sort of things is an idea of an area law. Emerges in various different aspects of physics, from black holes to sort of quantum many-body systems, all sorts of things, where the idea is whatever you're looking at in terms of information follows boundary physics and doesn't care so much about what's going on deep in the bulk of your system. In terms of entropy, we usually think of it as whatever information was past the boundary, we now don't have it, so information is gone, and the information at the boundary is dominating what we know about the outside because the boundary cuts our space. In terms of mutual information, what you normally do is you'll define a region A and region B, and you can ask how much does A know about B, depending on the size of the boundary that you allow between them or their volume. And if area law is being followed, then you find that mutual information is sensitive to the area between A and B, but not so much the volume of each. B could extend far over to this side of the slide, and A is not really going to care about what's going on over here.
But okay, so that's the information, and we've heard a lot today about quantum field simulators for gravity purposes, for the Unruh effect, things like this. Why do I want to do information in these systems? And I kind of have two answers. One is I want to use analog simulators to help what we know about information, and one is I want to use information to help us understand our analogs. On the left-hand side, information theorists over the last decades have come up with a lot of these predictions, these area laws, entanglement predictions, thermalization of information, scrambling. But they hold in regimes where we can do theoretical predictions or numerical simulations of them. If you have a macroscopic quantum system that's strongly interacting, that's driven far from equilibrium, not much is known, neither theoretically nor numerically. Whereas analog simulators, in principle, allow you to reach those sort of regimes and investigate what how information behaves when you do. On the other hand, information theory has these lovely predictions, things like area laws, where, for example, mutual information area law, like I said, it's sensitive to the boundary physics. So if you move the boundary, which changes the volume of A or B, in this case from one dimension, mutual information doesn't care. But if you don't have an area law, you have a volume law, mutual information responds a lot. This sort of stuff occurs, but it occurs under specific conditions. Then it occurs when correlations in your system are short-ranged. And that already tells you something about your system. Why are they short-ranged? Is it because the system has an effective mass? Is it because it's thermal and the thermal decoherence is happening? Has it gone through some sort of a localization stage? So you can learn a lot about your system in this way. The other example could be, for example, something like environment interactions. Information theory tells you a lot about how systems can interact with environments, how much they can share information, how much heat does that cost, things like this. And if we can track this information in a system, between a system and an environment, we could learn about how this interaction with an environment could be described. All I'm trying to say on this slide is I believe there's a lot of mutual benefit for combining these two fields, especially experimentally. But to do this experimentally, you need to know the state. Which, okay, if you have a classical system and it's simple, say you have a dice, you have some dice and it's got 6 sides on it, and you can toss it 1,000 times and you can compute this probability distributions, then you can do the trivial computation of entropy and information, things like this. But if you have something like the weather, tossing the weather 1,000,000 times and collecting probability distribution isn't really an option. But there are, since the 70s or better, since the late 2000s, methods to estimate these quantities, like entropy and information, directly out of data without resolving the probability distributions. Here I'm having a little icon to summarize. A lot of them are based on things like algorithms of neighbor searches. So you can do a lot of this even if you can't resolve the probability distributions super well. In the quantum case, you have a similar scenario. You need the state of the system. If you have a small quantum system or not many degrees of freedom, you can do that. You could also try to estimate the information without reconstructing the density matrix of the system in full, which you can try, but in quantum systems it's very difficult to do. Only in small Hilbert spaces and small number of spatial degrees of freedom is this ever possible. If you have something like a quantum fluid that we're interested in, not much you can do. There's been a paper in 2023 from the people in Vienna where they, using some heavy theoretical modeling, they could reconstruct the covariance matrix over time and compute these sort of mutual information, entropy, and things like this. So they find that entropy grows linearly with the size of the subsystem A, and the mutual information doesn't change. So it's like a volume law of entropy, but an area law of information. This was nice, and you could do it in a 1D quantum fluid with a particular boundary condition, in a particular state, with a particular model for its dynamics, in a particular parameter regime. If you want to do something more, we're kind of stuck. So the work that we want to do is measure these sort of things in our simulators. You've heard already a lot about them, so I'm just here. I have another photo of our fridge. Majority of that is cooling infrastructure. Here we have the experimental cell. The experimental cell has a window at the top and bottom that we can shine a laser through to watch the superfluid inside. Inside we have the superfluid sort of resting around a perimeter and coating with a thin film everywhere around the cell that produces this thin film on the window that we can pass a laser through as part of an interferometry scheme and image these waves. And as you've heard in previous talks, we have already some measurements of these waves, and we can start controlling how thick they are and all these things. Now these thin films, just as a quick summary, they have some interesting physics on their own. When they are cold enough and they are thin enough, first of all, the effective gravity is crazy. These waves look kind of like ripples. Okay, this is a sort of artist impression, it's not a real film, but these waves are already very extreme in that the effective gravity, for example, can be as strong as that of the surface of the sun, and then you've got ripples on there. So it's already very extreme scenarios if you think about it this way. The other thing is you don't have a separation between what's my bulk of a fluid and what's an interface of a fluid. If you have a photon inside of the bulk, it also excites an interfacial wave. So this is called the third sound, in these third sound waves that we're looking to image. The other nice thing is that this interface is basically completely viscosity free, and if your noise sources aren't absolutely crazy, you can linearize it and find, as in the previously alluded to papers, a linear model for the dynamics, which for the dynamics of the velocity potential and height perturbations are in equilibrium. So you can identify these thin films as simulators of field theories. And they're nice because they are naturally 2 + 1 dimensional. You can start playing with geometries on those. We already have space and time resolved measurements, so that's something lovely to have. And we are learning very quickly about how to control them and how to implement different states into them and things like this. So it's kind of an exciting time to be doing something like that. But to actually do the information studies we want, we need to be able to access information from watching waves. And that's not easy. We're working on some ways of doing it in general, and it's promising, but for now let's summarize what you can do when you have this linear model and Gaussian states of this linear model. If you have Gaussian states, you only need variance of the field. So you just need 2-point functions, and you can put them together into a covariance matrix. So 2-point functions of field height and field height cross terms. From that, there is known ways of computing entropy of your system. You can also split this covariance matrix up into spatial sectors, mode sectors, and compute entropies of these subsectors and find things like mutual information and play this game. But you need the covariance matrix. And we don't have access to all these 2-point functions. We have access to delta H with spatial and time resolution. So we need to figure out how to get that. To do this, we've considered the free theory that I've showed you on the last slide. We've contained it onto some sort of a volume of some shape with some boundary condition, which we've kept fairly general because superfluids can be complicated. And then we've expanded the field as well as the height perturbations, but I don't show it on here, in terms of modes that satisfy the natural geometry of that container. So here's an example for a circular container. You'd have Bessel modes, so it's a sort of representation of a Bessel function. And then with this, substituting into the previous Hamiltonian, you can find that these global modes follow a quantum harmonic oscillator. You can get the equations of motion and predict what the 2-point function of the height field looks like. So the left-hand side we can measure because we have spatially and time-resolved measurements of height perturbations. The right-hand side is some functions that we can compute based on the geometry that the system is in and the boundary conditions that it's exhibiting, and the block terms of the covariance matrix. So if you can collect data of the left-hand side, if you know these functions, you can invert this equation and find your covariance matrix. I say it like it's easy. We need to know the boundary conditions of a thin film superfluid helium, which is something we're still working on, and we need a lot of this data, which is something we're still working on. But in principle, you can then convert it, find this covariance matrix, and play the game of information theory. For now, I'll just show you some theoretical predictions of what we might expect from simulations when this happens. Say, for example, I have superfluid helium in a square container, and I call this region A, and I call this region B, and I just compute how much information is there between the two. I get this point for Neumann boundary conditions. I get this point for Dirichlet boundary conditions. And I carry this on. When I move the boundary, I don't change the size of the boundary, so that area between the two stays the same, but the volume changes. And I see that mutual information basically doesn't respond, and where it does sort of curve off at the edges, it fits the finite size corrections to area laws. So mutual information can be shown to follow area laws in these states. You can also define A and B as an equal slice of your system, and then instead of changing the volume and keeping the boundary the same, you can keep the volume the same, but undulate the boundary. Now you're increasing the area while keeping the volume constant, and you can show that mutual information increases sublinearly with increasing boundary area. So again, showcasing mutual information area law. Again, this is something that we're working towards measuring, but we're kind of experimentally getting there now. So just quickly for the next, apparently 15 seconds, but I will run over time into questions a little bit. What else are we wanting to do with this? The other things we're interested in doing is tracking information over time. So, for example, when we in this other simulator, we have a giant quantum vortex and ripples around it that experiences space-time as if around a black hole. Experimentally, it was found that there's super radiant instabilities in here that resemble something like a black hole bomb, where one mode will become unstable and grow exponentially until it saturates when it non-linearly couples to other modes. And within this, we're trying to measure the correlation functions and information between these different modes as they non-linearly interact through the instability. Also, as Breagh alluded to, I'm chasing her for more data from the shaker because we want to be looking at not just the correlation functions, but also transfer of information between modes in this effective field theory. And we have some preliminary results on how this information evolves over time. We also want to play with manipulating this information rather than just watching what it's doing. One way to do that is locally. We're designing some experiments in which we could, onto our thin film being imaged by a green laser, we could introduce a red laser as a pulse for a short amount of time, and then ask at a different region B, away from that pulse at some time t, how much information does it contain? So how much information was transmitted through the quantum field, and how much can you optimize it based on what this input pulse was? So this is something we're playing with right now, and also we're looking at how to manipulate information globally. For example, if you look at the speed of sound and the third sound, speed of the sound of these third sound waves, it depends on magnetic and electric fields, and we found that we can tune these electric and magnetic fields in such a way that the speed of sound exponentially decays, so that our height and velocity potential simulate free scalar fields now in an expanding spacetime. So we can start looking for phenomenology like mode freezing or some fun instabilities and track information within those. We're already designing experiments that would be capable of implementing these B and E fields and finding parameter regimes numerically where we do find things like mode freezing and instabilities. So with that, I'll just leave a slide of everyone involved, and thank you.
Thank you, Maciej. We have time for 1 or 2 questions.
So if you can build the covariance matrix associated with, say, local regions of the field, then you can literally ask any kind of question. So for instance, you can ask about how much entanglement is there between 2 regions or anything like that.
Absolutely.
Have you looked into any of these? Like, it's are you literally just waiting to have the data to sit down and do the calculations, or is there anything else that you require to be able to?
So theoretically, I have looked into this, and at the temperatures we're working at, and with the sort of noise sources we're working with experimentally, we don't expect yet to see any entanglement. So I've looked at things like negativity and discord, and none. Not at these sort of temperatures and not at these sort of noise sources. So for now, we would be looking at these emergence of area loss in a field theory in a quantum system, but information is kind of dominated by classical effects. To go towards, like, there's already plans to going colder and reducing the noise, especially once the labs are moved to Manchester and upgraded. And as we keep fighting this temperature down, we will eventually hope to see these sort of effects. And we've made some predictions as to what temperatures we require before we can conclude something like field entanglement. Off the top of my head, can't give it to you, but I can check it later.
But I mean, if you, for instance, just separate the whole thing into 2, now, well, the entanglement entropy, the entropy in our regions already witnessing entanglement with the other one, right? So of course, like, you can just basically consider like a thin strip between the 2 and things like that, right? So
in principle, you can, but I mean, the entanglement entropy of a half, for example, tells you about entanglement when the full thing is a pure state. If you have a full thing being a thermal state, it's more complicated. If you now have a noisy stochastic state.
I see. So even with the bipartition, you cannot confirm entanglement between the 2 regions, for instance?
Not in the states that we will expect it to have over the next, say, 2 years.
Oh, yeah, perfect. Thank you.
Okay, in the interest of time, let's all thank Maciej again.
Thank you.
Flip it somewhere.
Do you have a HDMI?
Yeah.
Can I plug the...
Yeah, sure.
not using it, I guess. That's fine.
Just in case you want to. Just this one here. Okay. Our next and last speaker of the day is Lucas de Paula, talking about non-axisymmetric analog black holes.
Okay, hello again. We survived the heat. So basically I'm going to talk about one of the works that I'm doing with the group. I'm basically just going to present the idea and the problem that we are tackling, how we are dealing with it, how we model it, and some perspectives, things that we want to do with this model. So we are interested in investigating what the break of axis symmetry does with an analog black hole. So I will start by talking about the model that we choose to do this analysis. People already talked about analog black holes, analog models here, so I'll try to be quick on this part. And then halfway through, I'm going to talk about how we model the event horizon in this case, because particularly we are interested in studying scattering problems, and we need to define the boundary conditions, and one of the boundary conditions is precisely at the horizon, so we need to model the horizon in this case. I'm going to show some plots of new geodesics, and I'm going to talk about some of perspectives of what we want to do with this. So there's two contexts in which we can extract motivation to do this kind of analysis. One is the astrophysical side of things. So we have the Kerr hypothesis that states that if a black hole is isolated, it is described by the Kerr metric. And we have the Hawking rigidity theorem that states that you have two options. If you have a stationary black hole, if it's static, it's spherically symmetric. It has a spherically symmetric causal boundary. And if it's rotating, it will be axis symmetric. So, for instance, the case of the Kerr black hole. So here's just an image of the Kerr black hole. It's nice, it's axis symmetric. There's all sorts of phenomena that happen surrounding this black hole, superradiance, quasi-normal modes, decay, Hawking radiation, etc. But the thing is that we know that in reality the black holes are not isolated. They have these so-called environmental effects that will disturb the space-time and might create these effective asymmetries in the system. You have the massive accretion disks, you have tidal forces that might disrupt the system a bit. So the question is how the axis symmetry break in this case will affect the phenomena that happens in these black holes. So this is one part of the motivation. The other part is related to the analogs. Because we have this way of measuring phenomena associated with black holes in the lab, we might think of measuring how the break of axis symmetry affect this phenomena within the analog black hole context. So people already talked about this, so we have that analog models, precisely in particular analog black holes, they will mimic black holes' kinematic features. So for instance, horizon, event horizon, and ergosphere. But we also know that when we implement this experimentally, we will always have an intrinsic asymmetry in the system because we have experimental limitations. So the question in this context is how can we measure the impact of these intrinsic asymmetries in the system, and maybe try to extract how this break of axis symmetry in this context will appear in the measurements, will influence the noise, or will influence the effects that we're trying to study in this context. So just quick in this part then, we have that if we want to study perturbations propagating through fluid flow, the velocity potential psi will be governed by, of the perturbations will be governed by Clyde-Gordon equation for massless scalar fields, and in a background metric that is given in terms of the properties of the medium, properties of the fluid in this case. So the particles of the fluid are going to couple with flat space-time, but the perturbations, they're going to couple with a curved space-time, which is given in terms by this metric. So they're going to perceive the medium as a curved space-time. So this effective metric, it's written in terms of the wave velocity, the background density, and the velocity profile of the medium. So by tailoring the velocity profile, you can build all sorts of systems. For instance, if you have within your system a region which is supersonic, the perturbations that propagate with local wave velocity, they're not going to be able to counter-propagate the flow, and you establish an acoustic horizon there. And then you can expect to have phenomena that are associated with event horizons in the system as well. So the first time that someone related this to, for instance, Hawking radiation was Professor Unruh in the seminal paper in which he proposed that somehow Hawking radiation could be measured in these systems. So what we're going to do is that we're going to pick a particular model for this fluid flow, which is the draining bathtub model. So this was proposed in 1998 by Matt Visser. So you have this velocity profile that has a draining parameter and you have a rotation parameter. So when you plug this into that metric, you get this line element that's going to be perceived by the perturbation. So you have an analog of a rotating black hole. So in this case, you can extract an analog event horizon, which is given by this term here, and analog ergosphere. So all phenomena that are associated with these two structures here, Hawking radiation for the ergosphere superradiance, you can expect to happen in this system as well. This was implemented by Silke's group in the laboratory, and they already measure superradiance and quasi-normal modes in these systems. So what we want to do now is to perturb this system and consider small asymmetries in it and try to model the break of axis symmetry in this kind of systems. So the way we do this is that we consider a new profile velocity which has now angle dependence, which is modeled in terms of this parameter delta. Then when we plug this into that effective metric, we have this big line element here. I'm just showing this to emphasize that now the metric is going to depend on angle. So in this case, we have an analog rotating black hole. You have an acoustic horizon, you have an ergosphere, but it's not axis metric. So you can think of it as a counterexample of the Hawking rigidity theorem, because you don't have the angular killing vector anymore. But since this is not related to Einstein's equations, in the end, there is no problem with that. So from this geometry, you can extract an ergosphere, which is basically related to the time-like killing vector, and you also can extract an event horizon. So the challenge here is to model the event horizon in order to study scattering problems in the system. So now the event horizon is going to be angle dependent, and the way that we model this event horizon is that we begin with an implicit function of two variables, r and phi. So the horizon is going to be a surface level defined by this function equals to 0. So because r is going to be equal to this r capital R, which is indeed the horizon, you have a normal vector to the surface, and you can calculate the 4 vector of the surface, and you impose that this null vector, normal vector to the surface, is null on the effective geometry that is modeled by the fluid. So this is the condition to get the horizon. You just calculate the normal, contract the normal vector of this implicit unknown surface, and you state that this is 0 in the metric in the background metric. When you do this, you get this equation for r capital R. This is a nonlinear differential equation for R, and when you solve this, you get your event horizon. So there are different ways of tackling this problem. You can try to solve this numerically, but the way that we first try to tackle this is by doing a perturbative approach, considering that this break of axis symmetry is small. So we're going to say that the event horizon in the end is just the horizon of the unperturbed system. Here I set the velocity, the wave velocity equals to 1, plus deformation that is angle dependent, and it is has this coefficient here, delta. So if we say that this deformation is much less than the unperturbed horizon, we can plug this into that equation and we get an analytical function for the event horizon up to first order on this parameter here. So as you can see now, the horizon in this system is angle dependent, but you have for this particular model in the denominator here of this deformation function, the parameter of the rotation and the draining. So you can expect if you you set this to a fixed value and you increase rotation, then the system becomes less and less asymmetric. So this is just a visual way of a visual plot. So in the left-hand side, you have the analog black hole for c equals to 1 and d equals to 1. You have this, in the background, this gray dashed line, which is the unperturbed horizon. And as you increase the perturbation, you can see that the horizon starts to deviate from this original form. In the right-hand side is just set up with d equals to 1 and a fixed value for the perturbation. And as you can see, as we increase rotation, as I told you, you go back to the axis symmetric case. So once we have this, the idea is to use this form and to study superradiance and other kinds of problems and see how this break of axis symmetry will affect this phenomena. So I'm just going to show now some plots of geodesics that I did, just to give you a visual insight of things, of how new rays are going to propagate in these systems. So here you have the unperturbed, in the left-hand side you have the unperturbed case, you have this orange curve which is the horizon, you have the dashed orange curve which is the ergosphere, you have these co-rotating new rays coming from infinity, counter-rotating waves coming from infinity, and the ones that get absorbed by the black hole. When you turn on the break of axis symmetry, you have some sort of disruption, and this you can expect that these lines are going to be deformed a little bit. Another one is that if we consider a fixed source close to the black hole, you can see that for a particular configuration you have these closed orbits here, but once you turn on the perturbation that breaks the axis symmetry, you don't have this closed orbit anymore, circular orbits anymore, because you have an angle dependence in these rays, in the geodesics. So the perspectives of this is to first study superradiance. So because we have a metric that is angle dependent, once we start studying the wave equation, there will be mode mixing. So in the classical case of superradiance, you send a wave with a particular azimuthal mode, and in the axis symmetric case, you get in infinity the same mode amplified. But because you have now angle dependence, the modes are going to be coupled, and you need to try and solve the coupled wave equation for the modes. So you can expect that there will be leakage of energy from this initial mode that you send into neighborhood modes. So another possible thing is to study the quasi-normal mode problem, try and implement this break of asymmetry in axis symmetry in an experiment, for instance in a draining bathtub, and try to study how this is going to affect the results for the usual phenomena that I studied there, and maybe Hawking radiation to also understand how this is going to affect Hawking radiation. So that's it. Thank you very much.
Thank you very much.
You've had this animation when you were increasing delta, and that was increasing the non-axis symmetric part. it looks like I was kind of hoping that it's a bit more jazzy than that, and it looks like it stays a circle but moves.
No, yeah.
It's not, is it?
No,
Because
it's not.
my question was going to be, could you find a coordinate transformation where all these effects, Hawking radiation, quasi-normal modes, etc., go back to what they normally are, or if it's actually deforming?
No, it's deforming, and you cannot see here, but it is indeed deforming. So the thing is that when you try to solve the wave equation, so in the metric, as I told you, there will be angle dependence there. You can try and do a coordinate transformation in which you set the boundary condition of the horizon in just a non-angular dependent coordinate, but then the coefficients of the wave equation are going to absorb this angle dependence. So in the end, you still have this angle dependence in the problem. So here is just, it looks like it's just like it's a circle that is moving down, but it's not. It's really being deformed.
So in an experimental proposal, how would you plan to introduce something like these perturbative effects?
Well, I need to talk with the experimentalists in the group to see, but I guess you can introduce a bump, for instance, in a draining bathtub in one particular side and see what happens. You can also look into the classical draining bathtub experiment, because there you also expect to have some asymmetries, right? You can never turn on turn off the asymmetries of experimental setup. So you always have this little delta there. So you can try to redo all the analysis of the experiments that were performed there and see if you can find an influence of this break of asymmetry there.
I'll go back since what Ilaria has asked you. So you're working with perturbations where you're considering that the event horizon is deformed. Have you considered what would happen if we didn't have an event horizon, but we still had an ergosphere that was deformed?
Yeah.
Because this would probably be closer to the experimental realizations, at least.
Yeah, that's a good idea. So there are different ways to introduce this break of axis symmetry. This is just one way. We do this because in this way we maintain the irrotational character of the fluid. So this is still irrotational, even though it depends on angle. So there are other proposals, like you can introduce an angle dependency in the background density of the fluid. You can try and do other things, and maybe one setup in which you have the event horizon, but the ergosphere is angle dependent somehow.
Let's all thank Lucas one more time. And now it's Rick's turn for some closing remarks.
All right, so let me start by thanking Ilaria and Maciej for bringing us all together here to listen to these amazing talks. So if we could please just give them a... Thank you so much, Maciej and Ilaria. So organizing the RQI circuit is not easy, but the local organizations are really, each one of them is a particular one. Not everyone goes out of their way to get lunch and coffee breaks and all these things. So really, thank you for that. And thanks, Silke, for providing us with, partially with this, and everyone that helped as well. So this was the 5th edition of the RQI Circuit 2026. We're going to have a 6th edition next week on Friday in Dublin, start in the morning. So feel free to watch. It's all live on YouTube. And with this, I don't know, give it back to the local organizers to give some final remarks, I'm assuming, about the dinner.
Yeah, okay. No particular final remarks other than to thank everyone for coming and for tuning in. For everyone that was registered coming in person, we have booked a table at a local place. It's called Navarro Lounge. So right after this, just join us there. The booking is for 5:30, so we should have plenty of time to make it there. It's only around the corner. And yeah, anything from you?
No. Thank you, everyone.
Thank you.